Look up at the night sky. For a moment, let your eyes adjust, not just to the darkness, but to the sheer scale of what you're seeing. Each tiny, glimmering point of light is not just a star, but often an entire sun, a solar system, a cosmic island. And yet, for all that breathtaking grandeur, the most profound, the most truly awesome secrets of the cosmos are not found in the light, but in the absolute, utter darkness. What if I told you that hidden within the hearts of most of those distant galaxies, including our own Milky Way, lurk cosmic monsters of such incomprehensible size and power that they could swallow our entire solar system whole without so much as a burp? These are not the black holes of science fiction. These are the universe's largest supermassive black holes, and their existence challenges everything we think we know about space, time, and reality itself. This journey we are about to take together isn't just a list of facts and figures. It is a voyage to the very edge of human understanding, a deep dive into the most extreme and enigmatic objects nature has ever conceived. We are going to explore the cosmic behemoths that anchor galaxies, whose gravitational pull is so fierce that not even light can escape their grasp. We will confront scales that dwarf human imagination, where a single object can contain the mass of billions of suns squeezed into a singularity smaller than our solar system. The sheer violence and majesty of their existence, the way they warp space-time, tear stars to shreds, and power the most luminous objects in the universe, paints a picture of a cosmos far more dynamic, far more terrifying, and far more beautiful than we could have ever dreamed. So, prepare to have your mind expanded and your perspective shifted. Over the course of this video, we will unravel 30 incredible facts about these gravitational titans. We will witness their birth, chart their growth, and peer into the mysterious physics that governs their event horizons, that point of no return from which nothing, not even information, can ever come back. This is an exploration of the ultimate limits, a story written in gravity and shadow, and it promises to reveal a universe that is stranger, more violent, and more wondrous than any fiction. The journey to understand the universe's largest black holes begins right now. To truly grasp the nature of these cosmic giants, we first need to understand what sets them apart from their smaller cousins. You've likely heard of black holes formed when massive stars collapse at the end of their lives. These are stellar mass black holes, and while they are fascinating and powerful in their own right, they are mere pebbles compared to the mountain ranges we're discussing. A typical stellar black hole might be 5, 10, or even 50 times the mass of our Sun. A supermassive black hole, on the other hand, operates on a completely different plane of existence. We're talking about objects that contain the mass of millions, even billions of suns, all compressed into a single gravitational point. Let's try to put that almost mythical number into perspective. Imagine taking our entire solar system, the Sun, all the planets, every asteroid and comet, and then replicating it a billion times over. Now, crush all that matter down into a region of space that is still smaller than the orbit of Neptune. The gravitational force created by such an incomprehensible density is what defines a supermassive black hole. Their location is just as significant as their mass. These are not nomads wandering the cosmic voids. They are the anchors, the gravitational hearts, at the very center of almost every large galaxy we have observed. Our own Milky Way galaxy, a vast spiral of hundreds of billions of stars, revolves around its own supermassive black hole, a relatively quiet giant known as Sagittarius A star. The relationship between a galaxy and its central black hole is one of the most profound and active areas of modern astronomy. It's not merely that the black hole sits there and the galaxy spins around it. The two are intricately linked in a cosmic dance, with the black hole's growth and activity influencing the evolution of the entire galaxy around it. Some of these supermassive black holes are dormant, like a sleeping dragon, while others are actively feeding, unleashing titanic energies that can outshine every star in their host galaxy combined. This sheer scale of power and influence is what makes them so central, quite literally, to our understanding of how the universe is structured on the grandest of scales. So if our own galactic center black hole, Sagittarius A star with its 4 million solar masses, represents a quiet giant, then we must now turn our attention to a true Leviathan, an entity that redefines the upper limits of what we thought was possible. This brings us to Fact 2, and the current heavyweight champion of the known cosmos, a black hole known as Ton 618. To call Ton 618 merely supermassive feels like a profound understatement. Astronomers sometimes use the term ultramassive for such colossi, and for good reason. While our galaxy's black hole has the mass of millions of suns, Ton 618 contains the mass of approximately 66 billion suns. Let that number settle for a moment. 66 billion. It is a figure so vast it becomes almost meaningless without a tangible comparison. Picture every single star in our entire Milky Way galaxy, a collection of between 100 and 400 billion stars. Ton 618 possesses a mass equivalent to a significant fraction of all of them. Yet this incomprehensible amount of matter is not spread across 100,000 light-years of space. It is concentrated, crushed into a singularity contained within an event horizon so enormous that it constitutes a sphere with a diameter larger than our entire solar system. If you were to place Ton 618 where our Sun is, its event horizon would easily swallow every planet, every asteroid, and even the distant Kuiper belt, extending out past the orbit of Pluto. But its immense gravity is only half the story of its fame. Ton 618 is not a dormant monster. It is a glutton, a cosmic engine of almost unimaginable power. It is what we call a hyper-luminous quasar. A quasar, which stands for quasi-stellar radio source, is the intensely bright active galactic nucleus of a distant galaxy. This brilliance comes from the black hole's accretion disk, a vast, swirling maelstrom of superheated gas, dust, and shredded stars that are spiraling inward toward their doom. As this material is torn apart and accelerates to fantastic speeds, it generates immense friction and magnetic forces, heating it to temperatures of millions of degrees. This process converts matter into pure energy with an efficiency far beyond that of nuclear fusion, causing the region around the black hole to outshine the combined light of every single star in its host galaxy. Ton 618, from its perch over 10 billion light-years away, shines with the luminosity of over 100 trillion suns, making it one of the brightest single objects in the entire observable universe. We are witnessing, across a gulf of space and time, the spectacular and violent feast of the universe's most ravenous titan. Now, to truly appreciate the nature of a titan like Ton 618, we need to move beyond just its staggering mass and confront the physical boundary that defines its power, the event horizon. This is not a solid surface you could touch. It's a mathematical membrane in space, a point of no return so absolute that it fundamentally reshapes our understanding of reality. Think of it as the ultimate one-way door. Every object with mass has a gravitational pull, but for a black hole, that pull becomes so overwhelmingly concentrated that at a specific distance from its center, the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing, not a single particle, not a glimmer of information, can ever come back out once it has crossed that threshold. This spherical boundary is known as the event horizon, and for a supermassive black hole, its size is almost beyond human comprehension. The size of this boundary is determined by what physicists call the Schwarzschild radius, named after the scientist who found this solution to Einstein's equations of general relativity. It's a straightforward calculation, but the results are anything but. The more mass a black hole has, the larger its event horizon becomes. For our Sun, if you could crush it into a black hole, its event horizon would be only about 3 kilometers across. For the 4 million solar mass black hole at the center of our Milky Way, Sagittarius A star, the event horizon would be roughly the size of Mercury's orbit around the Sun. But for Ton 618, with its 66 billion solar masses, the numbers enter the realm of the truly mythical. Its Schwarzschild radius calculates to a sphere with a diameter of over 390 billion kilometers. To put that incomprehensible scale into a familiar context, let's place this cosmic monster in our own solar system. The orbit of Pluto, often considered the outer boundary of our planetary system, is about 78 billion kilometers across on its long axis. The event horizon of Ton 618 would be a sphere 5 times wider than that entire orbital path. If this black hole were sitting where our Sun is, its dark, spherical boundary would extend outward, engulfing the orbits of Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and Pluto. It would swallow the entire Kuiper belt and stretch far out into the scattered disk of icy objects beyond. Every planet, moon, and comet within that immense volume of space would simply cease to exist from our perspective, having been lost forever behind the veil of the event horizon. But what does it actually mean to cross this boundary? The experience itself is a subject of both physics and profound mystery, a place where the known laws of the universe begin to break down. For an astronaut unfortunate enough to be falling feet first toward a supermassive black hole, the approach would be strangely serene at first, thanks to a principle called tidal forces. Because a black hole like Ton 618 is so immense, its gravity is spread over such a vast area that the difference in pull between your head and your feet would be negligible for a long time. You could cross the event horizon without even immediately noticing it visually. There is no flashing alarm, no physical barrier. Behind you, the universe you once knew would appear to carry on, though its light would become increasingly distorted, bent into a shrinking, brightening ring of all the stars and galaxies behind you. The true departure happens once you are inside. From your perspective, your journey continues toward the inevitable, unfathomable singularity at the center. But from the perspective of any outside observer watching you fall in, your story ends abruptly at the event horizon. Due to the extreme gravitational time dilation predicted by Einstein, your image would appear to slow down, becoming redder and dimmer until you simply faded from view, frozen in time just at the threshold. It's as if the universe itself paints a final, permanent portrait of you at the moment of crossing, while your own timeline continues on its one-way path. This is why we call it an event horizon. It is a horizon beyond which we can receive no information, no signals, no evidence that any events are taking place at all. It is the ultimate cosmic censorship, a boundary that not only traps matter and light, but also severs a connection to the rest of reality itself. Given that we can't see a black hole directly, measuring its mass might seem like an impossible task. How do you weigh an object that emits no light and is hidden behind an event horizon? The answer lies not in looking at the darkness itself, but in observing the brilliant, frantic dance of the stars and gas that are trapped in its gravitational grip. It's like trying to deduce the presence and strength of a magnet by watching how iron filings arrange themselves around it. For supermassive black holes, the iron filings are entire stars and vast clouds of glowing gas, orbiting the galactic center at speeds that defy imagination. One of the most reliable and direct methods involves meticulously tracking the orbits of individual stars that pass perilously close to the galactic center. Our own Milky Way provides the perfect laboratory for this technique. For decades, astronomers have trained powerful telescopes like the Keck Observatory and the Very Large Telescope on the heart of our galaxy, monitoring the motions of a specific group of stars known as the S-stars. These stars are caught in an extreme gravitational tango with Sagittarius A star. By plotting their positions over many years, we can map out their orbits with incredible precision. Some of these stars complete a single, incredibly fast orbit in just a handful of years, swinging around at speeds exceeding 10,000 miles per second at their closest approach. This is where a fundamental law of physics, formulated by Johannes Kepler in the 17th century, becomes our most powerful tool. Kepler's laws of planetary motion describe how objects orbit a central mass. His third law, in particular, provides a precise mathematical relationship. The square of a star's orbital period is proportional to the cube of the semi-major axis of its orbit. In much simpler terms, if you know how long a star takes to orbit and the size of its orbit, you can calculate the mass of the object it's orbiting. When we apply this to the S-stars whipping around our galactic center, the math reveals an inescapable conclusion. All of that incredible orbital motion is being driven by a single, incredibly dense object with a mass of about 4 million suns. There is simply no other plausible explanation for such rapid orbits confined to such a small region of space than a supermassive black hole. For more distant galaxies where we can't resolve individual stars, astronomers turn to another technique, measuring the velocity of the entire disk of gas and stars swirling around the center. Using spectrographs, they can detect the subtle red and blue shifts in the light from this material. The side of the disk spinning toward us has its light shifted to the blue end of the spectrum, while the side spinning away is shifted to red. By measuring the breadth of this shift, they can determine the rotational velocity of the entire galactic core. Just like with the individual stars, the faster that material is whirling, the more mass must be concentrated in the center to hold it in its orbit. This method is how we've been able to weigh the monstrous black holes in galaxies millions or even billions of light years away, building our census of these cosmic giants across the universe. But tracking the frantic orbits of stars and gas is one thing. Actually seeing the void itself is another challenge entirely. For decades, black holes existed as mathematical certainties in our equations and observational inferences in our data. But they remained fundamentally unseen, their true visage hidden behind the very nature of their light-devouring power. That all changed on April 10, 2019, when a global team of scientists unveiled an image that stopped the world in its tracks. It was a slightly blurry, fiery orange ring, resembling a celestial donut, but it represented one of the greatest achievements in the history of astronomy. This was the first direct visual evidence of a black hole's shadow, captured at the heart of a galaxy called Messier 87, 55 million light-years away. The subject of this portrait was the supermassive black hole known as M87 star. The scale of M87 star is difficult to overstate. While our own galactic black hole, Sagittarius A star, has a mass of 4 million suns, M87 star is a true behemoth, weighing in at a staggering 6.5 billion solar masses. To put that in perspective, that's over 1,600 times more massive than the black hole at the center of our own Milky Way. All of that immense mass is concentrated into a region of space that, while vast on a solar system scale, is an incredibly tiny target when viewed from 55 million light-years away. Resolving it was like trying to spot a bagel on the surface of the moon from Earth, a feat that required a telescope of virtually impossible size. This is where the true genius of the Event Horizon Telescope project comes into play. Instead of building a single planet-sized dish, which is an engineering impossibility, scientists created a virtual telescope as large as the Earth itself. They synchronized a global network of 8 existing radio observatories, from the high deserts of Chile and Hawaii to the mountains of Arizona and Spain, and even the frigid landscape of the South Pole. By having all these telescopes observe M87 star at the exact same time, and combining their data with atomic clock precision, they effectively created an instrument with a resolution power unmatched by any single telescope in history. The amount of raw data collected was so immense it couldn't be sent over the internet. It had to be physically shipped on hundreds of hard drives to central processing centers where supercomputers spent years correlating and reconstructing the final, iconic image. So, what are we actually seeing in that famous orange ring? We are not looking at the black hole itself, of course, since no light can escape from it. What we are witnessing is the black hole's silhouette, its shadow, etched against the brilliant backdrop of its own superheated accretion disk. Imagine a lighthouse in the middle of a dense, swirling fog. The light from the fog directly behind the lighthouse is blocked, creating a dark central region. That is the black hole's shadow, a region roughly 2.5 times the size of the actual event horizon. This shadow is caused by the black hole's immense gravity, bending the very paths of light rays and trapping those that pass too close. Surrounding this central darkness is the asymmetric, bright ring of the accretion disk. The gas and dust in this disk are orbiting at nearly the speed of light, and the reason one side of the ring appears significantly brighter is due to a relativistic effect called Doppler beaming. The material spinning toward us at such fantastic speeds has its light amplified and focused, making it appear brighter, while the material spinning away from us has its light dimmed and stretched. This lopsided ring of light is a perfect match for what Einstein's theory of general relativity predicted a black hole should look like, providing stunning visual confirmation of a century-old theory, and opening a new era of exploring these gravitational giants not just through their influence, but by gazing directly into their dark, beating hearts. We have been journeying across the cosmos to confront black holes of almost mythical proportions, but one of the most significant and revealing of these giants is, in fact, our very own galactic neighbor. Tucked away in the dense constellation of Sagittarius, a mere 27,000 light-years from Earth, lies the supermassive black hole at the heart of the Milky Way, known as Sagittarius A star. While its mass of roughly 4.3 million suns might seem almost modest next to a colossus like Ton 618, this proximity transforms it from a distant abstraction into a living laboratory, offering us a front-row seat to the dynamics of a galactic core. For many years, Sagittarius A star was an inferred presence, a ghost in the machine whose existence was deduced by the frantic orbits of stars around an invisible, massive object. But in May of 2022, the Event Horizon Telescope collaboration did it again, following their landmark image of M87 star by unveiling the first-ever picture of our own galactic center's black hole. While both images share a similar fiery ring structure, the two black holes could not be more different in their behavior. M87 star is an active, jet-spewing giant, while Sagittarius A star is far more quiescent, a sleeping dragon that only occasionally stirs. This difference in activity is precisely what makes having both images so invaluable. It allows astronomers to compare and contrast how black holes behave under different feeding conditions. Capturing this image was in many ways an even greater technical challenge than photographing M87 star. Although Sagittarius A star is over 1,000 times closer to us, it is also over 1,000 times less massive, meaning its event horizon appears roughly the same size in our sky. But there was a major complication. Our line of sight to the galactic center is heavily obscured by vast clouds of interstellar gas and dust, which scatter and blur the radio waves the EHT relies on. It is akin to trying to see a pebble at the bottom of a fast-moving, murky river. Furthermore, the material in Sagittarius A star's accretion disk is far more turbulent and changeable. The glow of the hot gas around it flickers and morphs on timescales of mere minutes, unlike the more stable flow around M87 star. This required the team to develop sophisticated new algorithms to average out this rapid variability and piece together a clear portrait from what was essentially a chaotic, swirling fog. The resulting image is a triumph of persistence and ingenuity. It shows a familiar yet profoundly intimate, bright ring of light encircling a dark central shadow. This ring is the direct visual evidence of photons whipping around the black hole's event horizon, their paths bent into a circle by the extreme warping of space-time. The dark central region is the black hole's shadow, about half the size of the shadow cast by M87 star, perfectly scaling with its smaller mass. This confirmation was a critical test for general relativity, demonstrating that Einstein's equations hold true for black holes of vastly different scales. Seeing this delicate structure, knowing it is the gravitational anchor for our entire galaxy, a vast pinwheel of hundreds of billions of stars drives home a humbling and powerful truth. Our cosmic home, for all its majesty, is not the center of the universe, but it does revolve around a silent, dark heart, a testament to the mysterious forces that shape all galaxies. That shadowy ring at the center of M87 and our own Milky Way represents an unfathomable concentration of mass, but it's the fiery, luminous halo surrounding it that truly reveals the raw power these objects can unleash. We've mentioned quasars in passing, but now we must confront them directly, for they are the single most powerful and persistent energy sources in the entire cosmos. A quasar, or quasi-stellar radio source, can outshine 1,000 galaxies, each containing hundreds of billions of stars, all from a region of space not much larger than our own solar system. For a long time, their nature was a profound mystery. They appeared as star-like points of light, yet their spectra revealed they were impossibly distant and moving away from us at tremendous speeds. The only conceivable engine capable of generating such staggering energy from such a small volume is the gravitational fury of a supermassive black hole in its most active feeding phase. The secret doesn't lie within the black hole itself. Remember, once matter crosses the event horizon, it vanishes from our universe, taking its energy with it. The phenomenal power of a quasar is generated just outside this point of no return, in a vast, swirling structure known as an accretion disk. Imagine a colossal, cosmic whirlpool, a maelstrom of gas, dust, and shredded stars spiraling inward at velocities approaching the speed of light. As this immense torrent of material is pulled inward by the black hole's overwhelming gravity, it doesn't fall in a straight line. Conservation of angular momentum forces it to form a flattened, rotating disk, much like water circling a drain. Within this disk, the particles of matter are packed together with unimaginable density, constantly jostling, colliding, and creating immense friction. This friction, combined with the unbelievable shear forces generated by the differential rotation of the disk, the inner parts orbit much faster than the outer parts, heats the material to temperatures we can scarcely comprehend. We are not talking about thousands or even millions of degrees. The inner regions of a quasar's accretion disk can reach temperatures of millions of degrees, hot enough to strip atoms down to their constituent particles and turn matter into a superheated plasma. At these extreme temperatures, the material doesn't just glow with visible light. It radiates ferociously across the entire electromagnetic spectrum, from low-energy radio waves through visible light, and up to incredibly energetic X-rays and gamma rays. This process of converting gravitational potential energy into radiant energy through friction and compression in the accretion disk is staggeringly efficient. While nuclear fusion, the process that powers stars, converts only about 0.7% of mass into energy, the accretion onto a black hole can achieve an efficiency of up to 10% or even more. This is why a single quasar can produce more light than every star in its host galaxy combined. It is a conversion factory of matter into pure energy, operating at the very limits of physical law. The brilliance of this process is what allows us to see quasars from the farthest reaches of the observable universe. They act as cosmic lighthouses, their beams piercing through billions of light-years of space and time. When we observe a quasar, we are witnessing a supermassive black hole in a state of extreme gluttony, a period when it is consuming a tremendous amount of surrounding material. This is not a gentle process, often triggered by galactic collisions or the disruption of a star venturing too close. The influx of fresh fuel causes the black hole to awaken from its slumber and ignite its quasar engine, flooding its host galaxy with radiation so intense it can halt star formation and blow away vast clouds of gas. This intimate feedback loop, where a black hole's feeding frenzy directly shapes the evolution of its entire galaxy, is one of the most critical discoveries in modern astrophysics, revealing that these dark hearts are not just passive occupants but active architects of the cosmic structures we see today. This deep connection between a galaxy and its central black hole is perhaps the most startling discovery in modern cosmology. It's not just that every large galaxy seems to have one, it's that the black hole's mass is inexplicably linked to the large-scale structure of the galaxy itself. Astronomers have found a remarkably tight correlation. The more massive a galaxy's central bulge, that dense, spherical swarm of older stars at its core, the more massive its supermassive black hole. This isn't a loose trend, it's a precise mathematical relationship. A galaxy with a large bulge will have a proportionally large black hole, while a galaxy with a small bulge will have a smaller one. This discovery was like finding that the size of a city's central park is always perfectly proportional to the size of the engine in the mayor's car. It hints at a fundamental, shared growth process, a co-evolution that is written into the very fabric of the cosmos. But how could an object so tiny, relatively speaking, influence a structure a billion times larger? The black hole's event horizon is a minuscule point when compared to the vast expanse of its host galaxy. The answer lies not in the black hole's constant gravitational pull, but in its rare, violent outbursts of energy. During its active quasar phase, when it is feasting on vast quantities of gas, the black hole doesn't just consume matter. It also fires colossal beams of energy and matter back out into the galaxy. These are the spectacular astrophysical jets, which can stretch for hundreds of thousands of light years, far beyond the galactic boundaries. These jets and the intense radiation from the accretion disk pour a phenomenal amount of energy into the surrounding interstellar medium. This energy acts like a cosmic hurricane, heating up the vast reservoirs of cold gas, the raw material for new stars, preventing it from cooling and collapsing to form new stellar nurseries. This process is known as feedback, and it's the key mechanism that links the black hole's appetite to the galaxy's destiny. Think of it as a cosmic thermostat for star formation. When the black hole feeds too greedily, the resulting outpouring of energy blows away the gas and shuts down its own food supply, effectively putting the galaxy on a diet. This feedback loop regulates the growth of both the black hole and the galactic bulge. Without this mechanism, galaxies might continue to form stars uncontrollably, growing far larger than they appear today. Instead, the supermassive black hole acts as a stabilizing force, a built-in governor that prevents the galaxy from becoming too massive. This explains the correlation. The black hole and the bulge grow in tandem, with the black hole's own growth ultimately putting the brakes on the formation of the very bulge it is linked to. They are partners in a cosmic dance, one that dictates the life cycle of stars and the ultimate size and shape of the galaxy we see. Even as we uncover the intricate dance between black holes and their host galaxies, a far more profound and ancient mystery emerges from the depths of cosmic time. We now have to confront a puzzle that challenges our understanding of how the universe built its first structures: the mysterious and incredibly rapid formation of these supermassive giants. Astronomers using our most powerful telescopes have made a startling discovery. They have detected fully formed supermassive black holes, some with masses exceeding 1 billion suns, shining as brilliant quasars when the universe was less than 1 billion years old. In cosmic terms, this is like finding a skyscraper in the middle of a landscape that should only have simple mud huts. The universe simply did not have much time to build something so colossal, and this presents one of the most active and compelling frontiers in all of modern astrophysics. So, how do you grow a billion solar mass black hole in under a billion years? The conventional method we discussed for stellar mass black holes. The collapse of a single, massive star is far too slow and inefficient to account for these early behemoths. A star, even a very large one, might leave behind a black hole of a few dozen solar masses. To reach a billion solar masses through successive mergers and steady accretion, the process would take much longer than the age of the universe at the time we are observing these quasars. The early black holes would have needed to start out with a significant head start, a massive seed unlike anything forming in the modern universe. This has led scientists to propose several radical and fascinating theories for the origins of these primordial seeds. One of the leading hypotheses is known as direct collapse. In this scenario, the very first generation of structures weren't individual stars, but immense, pristine clouds of hydrogen and helium gas. In the absence of heavier elements which act as a coolant, these clouds could have remained unusually hot and stable, resisting the fragmentation that would normally lead to the birth of many small stars. Instead of forming a star cluster, such a cloud, containing the mass of 100,000 suns or more, could have collapsed directly under its own immense weight. Without the outward pressure from nuclear fusion to halt the collapse, the entire vast cloud would have fallen in on itself, catastrophically and all at once, directly forming a single, massive black hole seed. This is not a star dying. It is a gas cloud skipping the stellar phase entirely and birthing a monster from its very inception. These direct collapse black holes, with initial masses already in the 100,000 solar mass range, would have had a tremendous gravitational advantage, allowing them to rapidly accrete surrounding gas and quickly snowball into the supermassive quasars we observe. A second major theory suggests that the seeds were indeed the remnants of the first, spectacularly massive stars, often called population 3 stars. These hypothetical stars were the universe's very first, composed purely of hydrogen and helium, and they are thought to have been behemoths in their own right, potentially reaching several hundred solar masses. Such massive stars would have lived fast and died young, burning through their nuclear fuel in only a few million years before collapsing into black holes of perhaps a few hundred solar masses. While smaller than a direct collapse seed, these stellar remnants could have grown rapidly if they found themselves in the perfect environment for growth: the dense, chaotic cores of the first protogalaxies. In these crowded stellar cities, frequent mergers between these early black holes could have quickly built up their mass. Furthermore, the rich supply of gas in these cores would have allowed for periods of hyper-efficient accretion, where the black hole fed at or even above its theoretical limit, a state known as super-Edmondson accretion. It is a cosmic race, where multiple smaller seeds merge and feast in a frantic environment, racing to become a supermassive entity in a remarkably short time. The truth is, both pathways, direct collapse and rapid growth from smaller seeds, might have played a role in different parts of the early universe. The environment was likely the deciding factor. A relatively isolated gas cloud might have taken the slower path of forming individual stars, but in the densest regions, where the gravitational pull of dark matter created deep potential wells, the conditions would have been perfect for the more dramatic direct collapse scenario to unfold. Unlocking this mystery is a primary goal for the next generation of observatories, like the James Webb Space Telescope. By peering back to the era of the very first galaxies and quasars, Webb is searching for the faint signatures of these primordial seeds and their host environments, hoping to catch them in the act of formation. Solving this puzzle is not just about understanding black holes. It is about deciphering the very blueprint of cosmic construction, revealing how the universe transitioned from a smooth, dark expanse into the structured, luminous cosmos we inhabit today. While we have marveled at the sheer scale of Ton 618, it is not alone in the pantheon of gravitational titans. To find another black hole that may truly rival its immense proportions, we must turn our gaze to a galaxy of equally staggering dimensions, IC 1101. Situated in the heart of the Abell 2029 galaxy cluster, over 1 billion light-years away, IC 1101 is a colossal lenticular galaxy that holds the title of one of the largest single galaxies ever discovered by volume. Its stellar disk spans an almost unimaginable 6 million light-years across, making it nearly 60 times wider than our own Milky Way. And at the heart of this cosmic metropolis lies a supermassive black hole whose estimated mass pushes the very boundaries of what we believe is possible. Determining the precise weight of this central monster has proven to be a significant challenge for astronomers, leading to a fascinating range of estimates. Unlike with TUN 618, where we can study the dynamics of its brilliant quasar, or our own galactic center, where we can track individual stars, IC 1101's black hole is more elusive. The methods used often involve analyzing the overall motion of stars within the galaxy's incredibly dense core or studying the properties of its surrounding gas. These observations have yielded a spectacularly wide mass range, with current estimates placing the black hole somewhere between 40 and 100 billion solar masses. That upper estimate is particularly staggering, as it would not just rival TUN 618, but potentially dwarf it, claiming the title of the most massive black hole known. Even at the more conservative end of 40 billion solar masses, this object is still an order of magnitude more massive than the black hole in M87 and 10,000 times more massive than the one at the center of our own galaxy. So, why is there such a wide margin of error? The uncertainty itself is a crucial piece of scientific data. It highlights the extreme physical conditions at play in such a massive system. The core of IC 1101 is an incredibly crowded and complex environment, a stellar swarm of immense density. Teasing apart the gravitational influence of the central black hole from the collective gravity of billions of tightly packed stars, dark matter, and surrounding gas is an immensely difficult task. The light we receive is an amalgamation of all these components, and astronomers must use sophisticated models to disentangle the signature of the black hole from the background stellar hum of the galaxy itself. This is the cutting edge of extragalactic astronomy, where each new observation and improved model helps to refine these colossal measurements. Studying such extreme objects is far more than just a record-keeping exercise for the cosmos. These behemoths serve as unparalleled natural laboratories for testing the fundamental laws of physics under conditions we could never hope to recreate on Earth. For instance, their immense event horizons provide a unique testing ground for Einstein's theory of general relativity. The way spacetime is warped around 100 billion, solar mass black hole is exponentially more severe than around a smaller, million solar mass one. By observing the orbits of stars or the behavior of light near these monsters, we can probe for any subtle deviations from Einstein's predictions, potentially uncovering clues to a deeper theory of gravity that unites general relativity with quantum mechanics. Furthermore, the very existence of black holes this massive challenges our theories of their formation and growth. The presence of a black hole weighing 100 billion suns so early in the universe's history would put immense strain on our current models of black hole seeding and accretion. How could an object accumulate so much mass in the relatively short time available? Did it form from an unimaginably large primordial seed? Or did it experience a period of hyper-efficient, runaway accretion that defies our current understanding of the Eddington limit? The search for answers to these questions drives the development of new theories and more powerful observational campaigns. Each day, a point from a galaxy like IC 1101 helps us refine our cosmic timelines and understand the ultimate limits of black hole growth, painting a more complete picture of how the most massive structures in the universe came to be. Consider for a moment the silent, invisible force that orchestrates the cosmos: gravity. We have explored how these supermassive black holes bend space and time into a deep well. But what happens when two such wells, two of the most massive objects in existence, decide to become one? Their final act of union does not unfold with a flash of light, but with a shudder that ripples across the very fabric of the universe itself. These are gravitational waves, the echoes of cosmic catastrophes first predicted by Einstein a century ago, and finally directly detected in 2015. While that first detection came from the merger of two stellar mass black holes, the ultimate gravitational wave events, the ones that would dwarf all others, are generated by the slow, inexorable dance and final collision of supermassive black holes. When two galaxies merge, their central supermassive black holes are drawn together by friction with stars and gas, eventually forming a binary pair. These two titans can orbit each other for millions of years, their immense masses churning the spacetime around them like a cosmic blender. As they lose energy by rippling spacetime itself, their orbit tightens and they spiral inward. The final moments before their merger are the most violent event since the Big Bang. When two black holes with billions of solar masses finally coalesce, they release more energy in a fraction of a second than all the stars in the observable universe combined release during that same instant. This energy is not emitted as light or radiation, but as a torrent of gravitational waves, traveling distortions in the geometry of space that stretch and squeeze everything in their path as they propagate outward at the speed of light. The frequencies involved in these colossal mergers, however, are far too low for our current ground-based observatories like LIGO and Virgo to detect. Their sensitive range captures the high-frequency chirps from stellar mass black holes, which orbit each other hundreds of times per second before merging. A binary pair of supermassive black holes, by contrast, might take years or even decades to complete a single orbit. Detecting their low, rumbling gravitational wave hum requires a completely new kind of observatory, one that operates not on the Earth's surface, but in the pristine quiet of space. This is the revolutionary mission of the Laser Interferometer Space Antenna, or LISA, a project led by the European Space Agency with significant NASA involvement, slated for launch in the mid-2030s. The LISA mission is a feat of astronomical engineering on a grand scale. It will consist not of a single telescope, but of three identical spacecraft, flying in a vast triangular formation millions of miles on each side, trailing behind Earth in its orbit around the Sun. Within each spacecraft, a perfect floating cube of gold and platinum, a test mass will drift in freefall, shielded from all external forces except gravity. Lasers will constantly beam between the three satellites, measuring the distance between these test masses with picometer precision, a distance so small it is a fraction of the width of a single atom. When a gravitational wave from a distant supermassive black hole merger passes through the solar system, it will subtly warp the space between the satellites. One arm of the triangle will momentarily lengthen while the other shortens, and the laser links will detect this infinitesimal change, revealing the passage of the space-time ripple. The data LISA collects will open an entirely new window onto the cosmos, allowing us to hear the universe in a way we never have before. It will effectively listen to the gravitational wave background of the universe, a constant choir of rumbles from merging supermassive black holes across cosmic time. By analyzing the frequencies and amplitudes of these waves, astronomers will be able to census the population of these binary giants, understanding how common they are and how they evolve. This will directly test our theories of galaxy formation, as every major galaxy merger should eventually lead to such an event. We might even catch the telltale signal of a black hole being kicked out of its galaxy from the asymmetric blast of gravitational waves during a merger, a phenomenon known as a recoil. The low-frequency gravitational wave spectrum holds the history of the universe's largest structures, a record of galactic collisions and black hole growth written not in light, but in the silent, rhythmic stretching of space itself. We've explored the immense gravity and explosive power of supermassive black holes, objects that seem to be the ultimate endpoints of cosmic evolution, permanent fixtures in the galaxy. But what if that permanence was an illusion? What if, on a timescale so vast it defies human imagination, even these gravitational titans have a finite lifespan? This brings us to one of the most profound and mind-bending concepts in all of theoretical physics, a discovery that forever changed our understanding of black holes: Hawking radiation. The man who unlocked this secret was, of course, the legendary physicist Stephen Hawking, who in the 1970s performed a brilliant feat of theoretical mathematics by marrying Einstein's theory of general relativity with the strange, probabilistic rules of quantum mechanics. To understand Hawking radiation, we first need to confront a fundamental principle of quantum theory: that empty space is not truly empty. What we perceive as a vacuum is actually a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the raw energy of the universe, borrowing energy from the vacuum for an impossibly brief moment before they collide and annihilate each other, paying back the energy debt and vanishing without a trace. This happens everywhere, all the time, even in the room you're sitting in right now. Ordinarily, this quantum flicker has no net effect, but something extraordinary happens when this process occurs right at the precipice of a black hole's event horizon. Imagine one of these virtual particle pairs springing into existence at the very boundary of the point of no return. In a fantastically rare but statistically inevitable occurrence, one particle of the pair falls across the event horizon, while its partner manages to escape outward into the universe. The particle that falls in has negative energy, and when it meets the black hole, it effectively reduces the black hole's total mass by a tiny, almost infinitesimal amount. Its escaped partner, now a real particle, carries positive energy away from the black hole into the wider cosmos. From the perspective of a distant observer, it appears as if the black hole has just emitted a particle. This is Hawking radiation, a slow, steady trickle of particles leaking out from a region from which nothing should be able to escape. Over eons, this process causes the black hole to lose mass, to slowly and quietly evaporate. This leads to a startling conclusion: black holes are not entirely black. They have a temperature and they glow, albeit with a faintness that is almost impossible to comprehend. The intensity of this Hawking radiation is inversely related to the black hole's size. For a small, stellar mass black hole, the radiation is relatively significant, and its temperature is quite high, meaning it would evaporate at a noticeable rate. But for the supermassive black holes that are the focus of our journey, the story is completely different. The temperature of a black hole is incredibly low for an object of such immense mass. A black hole the size of our Sun would have a temperature of only about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. Now, scale that up to a supermassive black hole like Sagittarius A, with its 4 million solar masses. Its Hawking temperature becomes almost laughably minuscule, a tiny fraction of a degree above the coldest temperature possible. This minuscule temperature translates into an evaporation time that is so long it becomes a philosophical concept rather than a practical reality. The time it takes for a black hole to completely evaporate via Hawking radiation is proportional to the cube of its mass. For a stellar black hole with the mass of our Sun, that time is an almost unimaginable 10 to the 67 years, a 1 followed by 67 zeros. Now, let's perform that calculation for a true supermassive giant like Ton 618, with its 66 billion solar masses. The numbers that result are so colossal they have no name in mathematics. We are talking about timeframes on the order of 10 to the 100th power years. To put that in perspective, the current age of our universe is only about 13.8 billion years, which is roughly 10 to the 10th power years. The evaporation time for a supermassive black hole is a number that is 10 to the 90th times longer than the universe has even existed. This means that for all practical purposes, and for any conceivable future we can envision, the supermassive black holes at the hearts of galaxies are effectively permanent structures. They will far outlive not just every star that will ever shine, but the very era of stars themselves, lasting deep into the theoretical cosmic end times known as the degenerate era and the black hole era. While Hawking's work revealed the profound truth that black holes are not eternal, their projected lifespans are so astronomically long that they will remain as the last, fading monuments in a dark and cooling universe, long after every other source of light has gone out. These immense jets of plasma, which can stretch far beyond their host galaxies, represent one of the most dramatic ways a supermassive black hole interacts with the cosmos. Yet, for decades, a fundamental puzzle remained. How does a black hole, an object defined by its all-consuming gravity, manage to fire out such colossal, focused beams of matter at nearly the speed of light? The answer, we now know, lies not just in gravity, but in another invisible cosmic force, magnetism. Recent observations, particularly from the Event Horizon Telescope, have peeled back the curtain to reveal that powerful, organized magnetic fields are the hidden architects behind these spectacular astrophysical jets. Imagine the chaotic frenzy of the accretion disk. We've described it as a swirling maelstrom of superheated gas, but that gas is so incredibly hot that its atoms are torn apart, creating a soup of charged particles known as a plasma. Where you have moving charged particles, you generate magnetic fields. In the turbulent environment around a black hole, these fields don't just sit idly by. They get stretched, twisted, and amplified by the disk's frantic rotation, like a cosmic dynamo. The Event Horizon Telescope's images of M87 star were not just about confirming the shadow. They also contained a treasure trove of information about the polarization of the light surrounding it. Polarization is a property of light that acts like a tiny compass, telling scientists about the direction and structure of the magnetic fields that the light passed through. Analysis of this data revealed a stunning picture. A powerful, ordered magnetic field structure wrapped tightly around the black hole itself. A magnetic cocoon that is both incredibly strong and remarkably organized. This magnetic field is the key to launching the jets. The standard model, often called the Blandford-Zenagic process, posits that the black hole's insane rotation, spinning its surrounding space-time along with it, acts like a gigantic battery. This spinning, when coupled with the intense magnetic fields threading the event horizon, generates a tremendous voltage. This electromagnetic energy can extract rotational energy directly from the black hole and use it to fling some of the infalling plasma outward, not in a messy explosion, but in two narrow, oppositely directed beams perpendicular to the accretion disk. It's a bit like twisting a rubber band until it stores immense energy, and then having it snap in two perfectly straight lines. The magnetic fields don't just provide the initial push, they also act as a highly sophisticated nozzle, collimating the outflowing plasma. They keep the jet incredibly tight and focused over hundreds of thousands of light years, preventing it from spraying out in a useless, wide-angle fountain. Without this magnetic confinement, the jets would lose their coherence and punch, and would never be able to travel the vast intergalactic distances we observe. The power of this magnetic mechanism is staggering. The jets from an active supermassive black hole can carry energy equivalent to the output of billions of stars, and they plow through the intergalactic medium like cosmic blowtorches. When these jets slam into the tenuous gas that exists between galaxies within a cluster, they can carve out enormous cavities, visible in X-ray observations, that are millions of light years across. This process dumps incredible amounts of energy into the cluster's environment. heating the gas and effectively putting a brake on the formation of new stars by preventing the gas from cooling and collapsing. This is a perfect illustration of magnetic feedback, a crucial extension of the black hole feedback we discussed earlier. It shows that the black hole's influence isn't just about radiation. It's also about these highly directed, magnetically driven outflows that can regulate the climate of an entire galaxy cluster, showcasing once again that the supermassive black hole, armed with its magnetic fields, is a dominant architect of the large-scale structure of our universe. But for all their immense power, the supermassive black holes that slumber quietly at the centers of galaxies are not always actively feeding on a steady diet of gas. Sometimes, their most spectacular and violent feasts are triggered by a single, catastrophic event, the unlucky passage of an entire star. Throughout a galaxy, countless stars orbit the central black hole, and most do so at a safe distance. But every so often, through gravitational interactions with other stars, one is nudged onto a highly elliptical orbit that sends it plunging dangerously close to the gravitational giant. When a star crosses this critical threshold, known as the tidal radius, it experiences a force so extreme that the star itself cannot hold together. This is the beginning of a cosmic cataclysm known as a tidal disruption event. The physics at play is a dramatic demonstration of the difference in gravitational pull across an object, what we call tidal forces. Think of it this way: the force of gravity gets stronger the closer you are to the source. When a star approaches the black hole, the side of the star facing the black hole feels a much stronger gravitational pull than the side facing away. For a supermassive black hole, this difference is colossal. The black hole's gravity doesn't just pull on the star, it actively tries to stretch it. The star, which is held together by its own gravity, is now caught in a cosmic tug of war it cannot win. Initially, it begins to stretch, elongating into a thin stream of gas, a process often called spaghettification. As it gets even closer, the tidal forces overwhelm the star's self-gravity, and it is literally ripped apart. The star is shredded from a sphere into a long, thin ribbon of superheated plasma, wrapping around the black hole in a chaotic stream. This violent dismantling is only the prelude to the main event. The debris from the shredded star doesn't all fall directly into the black hole at once. About half of the stellar material is flung outwards into the darkness of intergalactic space, lost forever. The other half is scattered onto a wide range of new orbits around the black hole, forming a sudden, temporary, and incredibly bright accretion disk. This disk is far denser and more chaotic than the steady-state disks we see in persistent quasars. The gas is fresh, rich in hydrogen from the star's interior, and it falls toward the event horizon at a ferocious rate. The immense friction and collisions within this newly formed disk heat the material to temperatures of hundreds of thousands of degrees, causing it to glow with an intense flare of radiation that can outshine the combined light of every star in its host galaxy for several months. For astronomers, witnessing a tidal disruption event is like catching a supermassive black hole in the act of a single, glorious, and violent meal. These transient flares are beacons that allow us to find and study otherwise dormant black holes in distant galaxies. By analyzing the light curve, how the flare brightens and then gradually fades over time, scientists can deduce the mass of the black hole and the nature of the star that was consumed. Each event is a unique natural experiment, offering a glimpse into the demographics of stars at the very centers of galaxies and providing crucial data on how black holes switch on and consume matter. It is a stark reminder of the dynamic and often dangerous nature of our cosmos, where even something as massive and stable as a star can be transformed into a brilliant, final flash of light by the unforgiving gravity of a dark heart. These tidal disruption events, where a star is shredded into a stream of hot gas, present a dramatic but ultimately straightforward story from the perspective of classical physics. The matter falls in, its energy is released, and what crosses the event horizon is gone forever. Yet, this very concept of gone forever conceals one of the most profound and contentious puzzles in all of modern science, a problem that strikes at the very heart of our understanding of reality. This is the black hole information paradox, and to grasp why it is so paradoxical, we need to consider two of the most successful but seemingly incompatible theories ever devised: general relativity and quantum mechanics. General relativity, Einstein's magnificent description of gravity as the curvature of spacetime, gives us a very clear, almost stark, picture of a black hole. The theory tells us that a black hole can be completely described by just three properties: its mass, its electric charge, and its spin. This is often called the no-hair theorem, implying a black hole has no other distinguishing features, no hair, no intricate details. If you were to take a copy of the complete works of Shakespeare, a grand piano, and a mountain of pure diamond, and you threw all of it into a supermassive black hole, what would happen? According to classical general relativity, the black hole would simply get a little more massive. Its event horizon would expand slightly, and that would be that. All the intricate information that made those objects unique, every word, every musical note, every atomic structure, would be utterly and permanently erased from our universe. The black hole would now be indistinguishable from one that had formed from an equivalent amount of pure hydrogen gas. From this viewpoint, information is not just hidden, it is destroyed. This, however, creates a direct and furious conflict with the foundational principles of quantum mechanics. In the quantum world, information is never truly lost. The universe, at its most fundamental level, is believed to be deterministic and reversible when it comes to information. This is a principle called unitarity. Think of it like this: if you could know the exact quantum state of every particle in a system at a given moment, the laws of physics should, in principle, allow you to rewind time and see exactly where everything came from. You could burn a book, and while you could never practically reassemble it from the ashes and smoke, the information about every letter on every page is still encoded in the state of all the particles, however scrambled. The information is transformed, but it is not destroyed. So, when a black hole seemingly annihilates information by swallowing it behind the event horizon, it violates this core quantum tenet. We are left with a fundamental contradiction. General relativity says information is lost forever in a black hole, while quantum mechanics insists that such a loss is fundamentally impossible. This paradox was brought into sharp focus by Stephen Hawking's own work on black hole evaporation. As we discussed, Hawking radiation causes a black hole to slowly lose mass and eventually evaporate completely. But here's the catch. Hawking showed that the radiation emitted is purely thermal. It is random noise, like the heat radiating from a hot stove. It contains no information about what fell into the black hole. So if a black hole forms, swallows a star, a planet, and a library, and then over eons evaporates away, all that is left is this faint, featureless glow of Hawking radiation. The original information about the star, the planet, and the library has apparently vanished from the universe. This presents scientists with a stark choice. Either our understanding of quantum mechanics is wrong, and information can be destroyed, which would overturn a century of physics, or our understanding of general relativity at the event horizon is incomplete. This crisis has spurred some of the most creative and mind-bending theoretical work in physics over the last few decades. One leading proposal suggests that the information isn't actually lost inside the black hole, but is somehow encoded on its two-dimensional event horizon. This is the holographic principle, the radical idea that all the information about a three-dimensional volume of space can be stored on its two-dimensional boundary, much like a hologram on a credit card stores a three-dimensional image on a two-dimensional surface. In this view, when matter falls into a black hole, it doesn't vanish into a singularity. Instead, Its information is smeared out and stored as a kind of ultra-dense code on the event horizon itself. Then, as the black hole emits Hawking radiation, this process is not random. The radiation subtly interacts with this encoded information on the way out, and over the entire lifetime of the black hole, the information is slowly and meticulously leaked back out into the universe, woven into the fabric of the escaping radiation. The information is never destroyed. It is merely scrambled in the most complex way imaginable, requiring a hypothetical decoder of infinite power to read it back. Another, even more contentious, idea involves a literal firewall. If information is to be preserved, some theorists argue that the event horizon cannot be the smooth, gentle gateway predicted by general relativity. Instead, it must be a searing wall of unimaginably high energy, a firewall that would instantly incinerate anything attempting to cross it. This would resolve the paradox by ensuring that information never actually enters the black hole. It is converted into energy at the boundary. However, this solution creates its own massive problem, as it blatantly violates the principle of equivalence from general relativity, which states that an observer falling into a black hole should not experience anything unusual at the event horizon. You can't have both a smooth space-time continuum and a raging firewall. It's one or the other. The debate over the information paradox is far from settled. It represents a fundamental frontier where our two greatest theories of reality collide, and resolving it will likely require a new, deeper theory. Perhaps a theory of quantum gravity that successfully merges the world of the very large with the world of the very small. The fate of information inside a black hole is not just an abstract philosophical game. It is a crucial test for the laws of physics as we know them. The answer will ultimately tell us something profound about the nature of reality itself, about whether the universe truly forgets, or if every single bit of information, from the birth of a star to the fall of a sparrow, is eternally and forever preserved in the cosmic record. But in our exploration of these cosmic extremes, from the stellar mass black holes to the supermassive behemoths, a crucial piece of the puzzle has remained conspicuously elusive. If stellar mass black holes are the pebbles and supermassive ones are the mountains, where are the boulders? This is the mystery of the intermediate mass black hole, an object with a mass ranging from roughly 100 to 100,000 times that of our Sun. Finding these missing links is not just about filling a gap in a catalog. It is one of the most active and exciting hunts in modern astronomy because it could finally unlock the secret of how the first supermassive black holes grew so big, so fast. The challenge lies in their very nature. Stellar mass black holes are often found when they are part of a binary system, pulling material from a companion star and emitting telltale X-rays. Supermassive black holes, by their very location at the dynamic centers of galaxies, reveal themselves through the frantic orbits of stars and gas. But intermediate mass black holes are predicted to exist in more isolated environments, like the dense cores of ancient globular clusters that orbit galaxies, or wandering through the halos of galaxies. They could be quiet, not actively feeding, making them incredibly difficult to spot against the vast, dark backdrop of space. Astronomers have had to become detectives, looking for subtle, indirect clues that point to their hidden presence. One of the most compelling methods involves tracking the motions of stars within a globular cluster. These clusters are spherical swarms of hundreds of thousands of ancient stars, all gravitationally bound together in a tight ball. By meticulously measuring the velocities of stars at the very heart of a cluster, scientists can look for the same telltale sign they used for Sagittarius A, stars orbiting an invisible, massive point. In several clusters, like Omega Centauri, observations have revealed that the central stars are moving far more rapidly than the collective gravity of all the visible stars can account for. The only plausible explanation is a dark, compact object lurking in the core, an intermediate mass black hole with the mass of tens of thousands of suns, acting as the gravitational anchor for the entire stellar swarm. Another tantalizing piece of evidence has come from a completely different type of signal: ultraluminous X-ray sources, or ULCs. These are objects located outside the galactic center that shine with the brightness of millions of suns, but only in X-rays. For a long time, their nature was debated. Could a stellar mass black hole be accreting material so rapidly that it becomes this brilliant, or are we seeing something more massive? The discovery of a few key ULXs, where the X-ray emission flickers in a specific way, has allowed scientists to weigh the central object. In these cases, the mass estimates consistently point to the intermediate mass range, suggesting we are witnessing a black hole of a few hundred or thousand solar masses in a rare and brilliant feeding frenzy. A cosmic snack that makes it visible across interstellar distances. Finding these missing links is absolutely critical for solving the puzzle of supermassive black hole growth. The existence of robust intermediate mass black holes would provide strong support for the bottom-up theory of growth, where smaller seeds merge and accrete over time. They would be the surviving stepping stones, the living fossils that demonstrate how a humble stellar remnant of a few dozen solar masses could, over billions of years of mergers and feasting, snowball into a billion solar mass giant. If, on the other hand, the hunt for them continues to come up mostly empty, it would lend more weight to the top-down direct collapse model, where supermassive black holes were simply born huge from the very beginning. Each new candidate intermediate mass black hole is therefore a precious data point, a clue that helps us rewrite the cosmic origin story of the most powerful objects in existence. This leads us to a fact that might just reshape your entire mental image of these cosmic giants, a clarification that is as crucial as it is counterintuitive. Despite their terrifying reputation, black holes are not cosmic vacuum cleaners, endlessly and greedily sucking in everything around them. The reality is far more nuanced and, in a strange way, more fascinating. Their immense gravity operates by the exact same rules as the gravity of the Sun, the Earth, or even the apple that famously fell on Newton's head. The only difference is the staggering concentration of that mass. Think of it this way: our Sun has a strong gravitational pull that keeps the planets in their orderly orbits. If you were to magically compress the Sun down into a black hole without changing its total mass, something remarkable would happen. The gravitational pull felt by the Earth, 150 million kilometers away, would be exactly the same. Our planet would continue to orbit this new, invisible point in space, tracing the same path it has for billions of years, now plunged into perpetual darkness but held in the same gravitational embrace. The danger of a black hole, therefore, isn't some mysterious, supernatural sucking force. The danger lies entirely in its ability to let you get unbelievably close to an immense concentration of mass. With an object like our Sun, you can't get very close to its center of mass before you're burned by its surface. But with a black hole, there is no solid surface to stop you. You can approach much nearer to the central point where all that mass is concentrated. It is this proximity, not a change in the fundamental laws of physics, that creates the point of no return. The event horizon is simply the boundary where the escape velocity exceeds the speed of light. Outside of that boundary, orbits are perfectly stable. This is why we see stars like the S-stars whipping around Sagittarius A at phenomenal speeds. They are in a stable, predictable dance with the black hole, held in orbit by its gravity just as the Earth is held by the Sun. They are not being slowly drained away. They are following the curved paths of spacetime, and they can continue to do so for eons, so long as they maintain a safe distance. A wonderful analogy to illustrate this is our own solar system. Imagine the Sun as a bowling ball placed on a stretched rubber sheet, creating a deep indentation. The planets are marbles rolling around in the curved fabric of that indentation. Now, if you were to replace that bowling ball with a tiny, incredibly dense object of the same weight, A black hole metaphor, the depth of the indentation at the distance of Earth's orbit wouldn't change. The marble would still roll around the same dip. The only difference is that the dip would get much steeper and deeper right near the center. You could roll your marble very close to that central pit, and if you had just the right speed, it could still orbit without falling in. But if you nudged it a little too close or slowed it down just a bit, it would spiral inward, crossing the point where the slope becomes too severe to ever climb back out. That critical slope is the event horizon. So, a black hole doesn't reach out and grab things. It simply creates a gravitational well so deep and so steep that once you cross its lip, there is no return. The universe isn't being hoovered up. It's simply a place where some valleys have become infinitely deep. Yet for all the talk of event horizons as the ultimate one-way street, there is another region surrounding a spinning black hole where the rules of reality become even more bizarre, and where the cosmos offers a potential loophole to its own grim laws. This is the ergosphere, an ovoid region of distorted spacetime that lies outside the event horizon, but inside a boundary known as the static limit. To understand its strange properties, we must first appreciate that the most realistic black holes in our universe are not static. They are dynamic, spinning at a significant fraction of the speed of light. This rotation transforms the black hole from a simple gravitational pit into a cosmic vortex, and it is this spin that carves out the ergosphere. The phenomenon at the heart of the ergosphere is one of the most dramatic predictions of Einstein's general relativity, an effect known as frame dragging. Imagine spacetime not as a static stage, but as a vast, viscous fluid. A massive, non-spinning object would simply create a stationary dimple in this fluid. But a spinning object, like our rotating black hole, acts like a spinning spoon stirring a pot of honey. It grips the very fabric of spacetime and drags it around in a relentless, swirling motion. Within the ergosphere, this frame dragging is so overpoweringly strong that it becomes impossible for any object to remain stationary. No matter how powerful your rockets, you cannot fight the current. You are compelled to move in the direction of the black hole's rotation. You are caught in a cosmic riptide from which there is no holding still. This leads to a truly surreal consequence. The very definition of standing still changes near a rotating black hole. For an observer far away, standing still means maintaining a fixed position relative to the distant stars. But inside the ergosphere, the frame dragging is so intense that spacetime itself is flowing faster than the speed of light relative to that distant observer. To even appear to be standing still from the outside, you would have to move against this current at faster than light speed, which is impossible. Therefore, within the ergosphere, everything, every particle, every photon of light, even the fabric of space itself, is forced to rotate with the black hole. It is a region where the universe mandates perpetual motion. It is within this whirling maelstrom that one of the most theoretically fascinating ideas in all of physics emerges: the possibility of extracting energy directly from a black hole. This is not science fiction. It is a rigorous consequence of the mathematics describing rotating black holes, a process known as the Penrose process, named after the physicist Roger Penrose who first proposed it. The principle relies on the unique properties of the ergosphere, where the relentless frame dragging creates a region of what we might call negative energy as seen from far away. Here is how it could theoretically work. Imagine an advanced spacecraft ventures into the ergosphere and releases a payload much like a probe, in a precisely calculated maneuver. The craft is designed so that one fragment of the payload falls into the event horizon, never to return, while the other fragment is flung back out of the ergosphere and recovered. The magic lies in the conservation of energy and momentum within this distorted spacetime. The fragment that falls into the black hole is deliberately sent in a direction against the black hole's rotation. Because of the intense frame dragging, this infalling fragment actually has negative energy relative to an observer at infinity. In a perfectly balanced transaction, the black hole absorbs this negative energy and negative angular momentum, which causes it to slow down its spin ever so slightly. To conserve the total energy, the fragment that escapes the ergosphere must carry away more energy than the original total energy of the entire payload before it was split apart. In essence, the spacecraft has stolen a portion of the black hole's rotational energy. It's as if you threw a heavy brick against the spin of a giant merry-go-round. The merry-go-round would slow down a tiny bit, and the brick you threw would come flying back at you with more speed and energy than you initially gave it. The black hole itself pays the energy bill, its immense spin being gradually braked by the process. While the engineering required for a spacecraft to perform the Penrose process is far, far beyond our capabilities, nature may already be doing something very similar on a grand scale. The incredible energies powering the relativistic jets we see shooting from active galactic nuclei are thought to be generated, at least in part, by a magnetic version of this same principle. The black hole's spin, transferred to the magnetic fields locked into its accretion disk, acts as a colossal slingshot, flinging plasma outward and converting the black hole's rotational energy into the directed beams that we observe across the universe. So, while the event horizon marks a boundary of ultimate consumption, the ergosphere represents a zone of immense possibility, a testament to the fact that even in the most extreme environments, the universe operates by a set of rules that can, with profound insight, be understood and perhaps one day harnessed. For a long time, our search for supermassive black holes was like looking for elephants and assuming they only lived in vast, sprawling jungles. We naturally focused our attention on the largest, most majestic galaxies, the cosmic metropolises like our own Milky Way, and the even larger Messier 87. It seemed logical that only such grand galactic structures could host and nurture these gravitational titans. But this assumption has been completely upended by a quiet revolution in observational astronomy, revealing that the seeds of cosmic power are far more democratically scattered throughout the universe than we ever imagined. We are now discovering that countless small, faint dwarf galaxies also harbor central black holes, and their existence is fundamentally reshaping our understanding of how the very first supermassive black holes came to be. Dwarf galaxies are the cosmic equivalents of small towns or villages. They are far more numerous than their giant spiral and elliptical cousins, but they contain only a fraction of the stars, perhaps a few billion compared to the hundreds of billions in a galaxy like ours. They are the building blocks of the universe, the primordial fragments from which the larger galaxies were assembled through eons of collisions and mergers. For decades, it was thought these modest galaxies were too small, their gravitational wells too shallow, to form or retain a supermassive black hole. They simply didn't have the immense bulge of stars that, in larger galaxies, so perfectly correlates with black hole mass. Finding a supermassive black hole in a dwarf galaxy would be like finding a jet engine inside a family sedan. It seemed like a mismatch of scale and purpose. Yet, that is precisely what astronomers have been finding. Using sophisticated techniques to scan the skies, they have identified the telltale signatures of active black holes in the hearts of these diminutive galaxies. Sometimes the clue is a flicker of X-rays from a tiny region at the galaxy's core, a sign of a black hole snacking on a wisp of gas. Other times, it's the subtle, rapid motion of stars near the center, indicating they are whipping around an invisible, massive object. The black holes found in these dwarfs are not the billion solar mass behemoths of giant ellipticals. They are more modest, typically ranging from a few thousand to a few 100,000 times the mass of our Sun. But their significance is monumental, far outweighing their modest size. This discovery presents a direct challenge to many established models of black hole formation. If supermassive black holes were exclusively tied to the massive bulges of large galaxies, their presence in tiny, bulge-less dwarfs is a major puzzle. It strongly suggests that the initial seeds for black holes were not rare, special occurrences, but were instead incredibly common in the early universe. Imagine the first galaxies being built. The new evidence implies that a vast number of these early dwarf galaxies, perhaps even the majority of them, were born with a central black hole seed already in place. This paints a picture of a young cosmos that was already peppered with these pockets of extreme gravity, long before the grand galactic structures we see today had even begun to form. The implications of this are profound for solving the mystery of how the first quasars grew so immense so quickly. If the early universe was a bustling landscape of dwarf galaxies, each carrying its own small black hole, then the pathway to building a supermassive giant becomes much clearer. When these dwarf galaxies collided and merged, their central black holes would have also merged, combining their mass. A larger galaxy formed from the merger of a dozen dwarfs would inherit a more massive black hole from the start, giving it a significant head start on its growth through further accretion. This building block scenario provides a natural and efficient mechanism for creating the billion solar mass quasars we see in the early universe. They didn't have to grow from a single, tiny seed in isolation. They could have been assembled from many pre-existing smaller seeds, like gathering many small streams to quickly form a mighty river. Studying these dwarf galaxies, black holes is like discovering a population of living fossils, offering us a unique window back in time. The large galaxies we see today are the products of a long and complex history of violent mergers and cannibalism. Their original central black holes have been built up, altered, and obscured by these events. But an isolated dwarf galaxy, one that has quietly drifted through cosmic history without undergoing a major merger, may still host a black hole that is largely unchanged from its primordial state. It is a relic, a pristine sample of one of the universe's first black hole seeds. By measuring the masses of these black holes and studying the properties of their host dwarfs, astronomers are essentially taking a census of the initial seeds, gathering the raw data needed to determine which formation theories, like direct collapse or the death of the first stars, were most prevalent in the dawn of time. This ongoing hunt is a primary scientific goal for the James Webb Space Telescope. With its unparalleled infrared vision, Webb is peering back to the era of the first galaxies and looking at nearby dwarfs with incredible precision, searching for the faint glow of these ancient black holes. Each new discovery adds another crucial piece to the puzzle. Helping us trace the lineage of the cosmic giants we find today all the way back to their humble origins in the universe's smallest galaxies. It reveals a cosmos where the potential for immense gravitational power was woven into the fabric of structure itself from the very beginning, a latent force waiting to be assembled into the dark hearts that now govern the fate of galaxies. While our eyes can only perceive the visible light from the tranquil stars, to truly witness the violent, high-energy drama swirling around a black hole, we need to look at the universe through a different kind of lens. This is where the Chandra X-ray Observatory enters the story, a flagship NASA telescope that has fundamentally reshaped our understanding of the cosmos by seeing the sky not in serene starlight, but in the searing glare of X-rays. Launched into orbit in 1999, Chandra was designed to detect photons with thousands to millions of times more energy than the light our eyes can see. It is in this high-energy realm that the most extreme processes in the universe announce themselves. And nothing is more extreme than the environment immediately surrounding a supermassive black hole. The reason X-rays are so crucial is directly tied to the physics of the accretion disk and jets. We've discussed how friction and shear forces heat the infalling gas to incredible temperatures, but to truly grasp the scale, we need to talk numbers. The inner regions of a quasar's accretion disk can reach temperatures of millions of degrees Celsius. At these phenomenal temperatures, matter doesn't just glow. It radiates its energy primarily in the X-ray part of the electromagnetic spectrum. Observing invisible light would be like trying to understand a blast furnace by looking at the dull, red glow of its outer bricks. Chandra, by contrast, allows us to stare directly into the white-hot heart of the furnace itself. It captures the direct emission from this multimillion-degree plasma as it spirals toward its doom, providing a clean, powerful signal of the black hole's feeding activity. But Chandra's vision goes far beyond just confirming that the gas is hot. It acts as a sophisticated cosmic thermometer and dynamics probe. By analyzing the spectrum of the X-rays, breaking down their specific energies and intensities, scientists can determine the precise temperature of the gas, its density, and even its composition. They can track how clumps of material orbit the black hole, revealing the powerful gravitational forces at work just outside the event horizon. For supermassive black holes that are relatively quiet, like our own Sagittarius A star, Chandra has been indispensable. Invisible light, our galactic center is completely obscured by thick clouds of interstellar dust. But X-rays, with their higher energy, can punch straight through this cosmic fog, allowing Chandra to monitor the occasional, faint X-ray flares that erupt when the black hole consumes a small asteroid or a wisp of gas, giving us a glimpse of the sleeping dragon's faint, restless stirrings. Perhaps Chandra's most breathtaking contributions have been in visualizing the colossal structures carved out by black hole jets. These jets, powered by the black hole's spin and magnetic fields, are not just beams of light. They are torrents of ultra-relativistic particles. When these particles slam into the much slower-moving clouds of gas that linger between galaxies in a cluster, the collision is so violent that it produces immense shock waves, heating the gas to tens of millions of degrees and causing it to glow brilliantly in X-rays. Chandra's iconic images of galaxies like Centaurus A and Perseus A reveal this in stunning detail. We see vast, balloon-like cavities, each large enough to swallow thousands of solar systems, hollowed out in the X-ray glowing gas by the relentless push of the jets. These cavities are a direct fossil record of the black hole's power, showing how it pumps energy into its surroundings on a scale that affects the evolution of the entire galaxy cluster, preventing the hot gas from cooling and forming new stars. This ability to see the interaction between the black hole and its environment has cemented Chandra's role in uncovering the feedback process we discussed earlier. By measuring the energy required to inflate these gigantic X-ray cavities, astronomers can make a direct calculation of the total power the black hole jet has delivered over its lifetime. The numbers are consistently staggering, often equivalent to the energy released by billions of supernovae. This provides the most direct, quantitative evidence that the energy output from a supermassive black hole is not just a spectacular side effect. It is a dominant regulatory force, a cosmic feedback loop that governs the growth of galaxies. Chandra has shown us that these dark hearts don't just consume, they also sculpt, using their high-energy outbursts to create magnificent structures and control the very climate of intergalactic space, leaving their mark written in the hot, X-ray glow of the cosmos for us to decipher. This brings us to a concept that is as elegant as it is unsettling, a principle that strips these cosmic giants down to their most fundamental essence. It's called the no-hair theorem, and while the name might sound whimsical, its implications are profound. In the language of physics, hair is a metaphor for any of the intricate, detailed information that makes an object unique. A planet has hair, its specific composition, mountain ranges, ocean currents, and atmospheric patterns. A star has hair, its complex internal fusion processes, magnetic field structure, and sunspot cycles. But according to this theorem, a black hole is the ultimate minimalist. It is bald, smooth, and utterly featureless, characterized by only three simple numbers: its mass, its electric charge, and its angular momentum or spin. Think of it this way. Imagine you could take the most complex, information-rich objects imaginable, a library containing every book ever written, a supercomputer storing the entire digital history of humanity, and a living, breathing rainforest ecosystem, and you throw all of it into a supermassive black hole. According to the classical view dictated by general relativity, the black hole would not care in the slightest. It would not record the stories in the books, the data on the hard drives, or the DNA of the organisms. It would simply respond by becoming very slightly more massive, its event horizon expanding by a tiny, calculable amount. Its electric charge might change if the infalling matter had a net charge, and its spin might be altered slightly by the angular momentum of the consumed material. But all the specific, messy details that made those objects what they were, the plot of a novel, the code of a program, the color of a butterfly's wings, would be irretrievably lost. The black hole that remains is completely identical to one that formed from the collapse of an equivalent amount of pure, undifferentiated hydrogen gas. It has no memory of its past. It is defined solely by its mass, charge, and spin. This radical simplification is a direct consequence of the unforgiving nature of the event horizon. Once matter crosses that boundary, it is causally disconnected from our universe. There is no mechanism in classical general relativity for any information about its prior state to be communicated back out. The no-hair idea is so powerful that it's often stated as a theorem. Black holes have no hair, meaning no other independent characteristics. This creates a universe with a surprising kind of cosmic democracy. No matter how complex or simple the object was that fell in, the resulting black hole is indistinguishable from any other with the same mass, charge, and spin. It's the ultimate eraser of complexity. But this beautiful, stark simplicity is also the very source of the black hole information paradox we discussed earlier. The no-hair theorem, born from general relativity, insists that information is destroyed. Quantum mechanics, with its unwavering principle of unitarity, insists it cannot be. This is the central conflict. Modern theoretical physics is grappling with this by questioning whether the no-hair theorem is the final word. The holographic principle, for instance, suggests that the information isn't actually lost. It's not stored inside the black hole, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface of the point of no return. In this view, the black hole does have hair, but it is exquisitely fine and holographic, stored in a way we are only beginning to comprehend. So, the no-hair theorem stands as a magnificent monument to the power of Einstein's theory, while simultaneously acting as a flashing neon sign pointing toward the next great revolution in physics, a theory that will finally tell us what truly happens to the story of a star after it vanishes from our view. Now, let's bring our focus back from the theoretical frontiers to a more practical distinction, one that explains why some of these cosmic giants blaze with the light of 100 trillion suns while others, like the one in our own galactic center, slumber in near darkness. This is the crucial difference between active and quiet supermassive black holes, a cycle of cosmic feasting and fasting that dictates the very personality of a galaxy. On one end of the spectrum, we have the dormant or quiescent black holes. Sagittarius A is the perfect example of this. It's a sleeping giant with a mass of 4 million suns, yet it emits only a faint trickle of radiation. This isn't because the black hole has stopped being a gravitational powerhouse. Its pull is as immense as ever. The quietness is because there is simply very little material for it to consume. The region immediately around it is relatively clean, a cosmic desert where only wisps of gas and the occasional stray star venture close enough to be captured. A dormant black hole is like a powerful engine idling, waiting for a fuel delivery that, for the moment, isn't coming. At the opposite extreme are the active galactic nuclei, or AN. This is a broad category that includes the most luminous objects in the universe, quasars, as well as other energetic cores like blazars and Seyfert galaxies. What unites them all is a supermassive black hole in the midst of a spectacular feeding frenzy. In these systems, the black hole is not idling. It is sitting at the center of a vast, chaotic, and brilliantly luminous banquet. Enormous quantities of gas, dust, and even entire stars are funneled into the accretion disk, creating that intense maelstrom of superheated plasma we discussed earlier. The conversion of gravitational energy into light and heat in this disk is so phenomenally efficient that the active galactic nucleus can outshine every single star in its host galaxy combined. The black hole itself is no more or less powerful than its dormant cousin. The only difference is the abundance of food in its immediate vicinity. An active black hole is an engine running at full throttle, its brilliance a direct measure of its gluttony. So, what triggers this dramatic shift from a quiet slumber to a brilliant, galaxy-defining awakening? The primary catalyst is almost always a cosmic disturbance, an event that disrupts the stable, orderly orbits of material in the galactic center and sends vast reserves of gas plummeting toward the waiting gravitational giant. The most common trigger is a galactic merger. When two galaxies gravitationally intertwine and slowly coalesce into one, their dance is anything but graceful. It is a violent process that sends shockwaves through their combined gas clouds, disrupting their orbits and driving immense amounts of this star-forming fuel directly toward the newly merged galactic core. It's like shaking a bag of marbles until a whole bunch of them fall straight into a central hole. This sudden, massive infusion of fuel ignites the quasar engine, and the black hole enters a period of hyperactive growth, shining with a ferocious intensity that can be seen across the universe. But mergers aren't the only way to wake the dragon. Even in an isolated galaxy like our own, smaller, more localized events can stir the black hole from its rest. A dense molecular cloud, wandering too close to the galactic center, can be torn apart by tidal forces and provide a substantial, though temporary, meal. We see evidence of this in the faint flares and flickers from Sagittarius A star, which astronomers interpret as it consuming small clouds or asteroids. On a more dramatic scale, a tidal disruption event, the complete shredding of a star, is like serving the black hole a single, magnificent, multi-course feast. It creates a sudden, brilliant flash of light as the stellar debris forms a temporary, super-bright accretion disk, providing a short-lived but incredibly intense period of activity. These events remind us that even the quietest black holes are never completely inactive. They are merely between meals, capable of flaring up at a moment's notice when the cosmic delivery van arrives. This cycle of activity and quiescence is not just a random on and off switch. It is a self-regulating feedback process that is fundamental to galaxy evolution. This brings us back to the concept of feedback we explored earlier. When a black hole enters its active quasar phase, the incredible outpouring of radiation and the powerful jets it generates have a profound effect on its surroundings. This energy blasts outward, heating the surrounding gas and driving powerful galactic winds. This process, while spectacular, effectively slams the door on the black hole's own food supply. The very energy it releases blows away the remaining reservoirs of cold gas, starving itself and eventually forcing it back into a dormant state. It's a cosmic case of overindulgence leading to a forced diet. The galaxy then enters a period of quiescence, allowing the surrounding gas to slowly, over millions of years, cool and settle back toward the center, potentially setting the stage for the next feeding frenzy. This elegant feedback loop explains why we don't see galaxies with endlessly growing black holes. They possess their own built-in thermostat, a cycle of feast and famine that keeps both the black hole and the galaxy's star formation in a delicate cosmic balance. Yet, the very existence of a cosmic titan like Ton 618, with its 66 billion solar masses, forces us to confront a deeply fundamental question. Is there an upper limit to how large a black hole can become? We are venturing beyond merely cataloging cosmic curiosities. and into the realm where these gravitational behemoths begin to strain the very fabric of our physical theories. While there is no known law of physics that explicitly states a black hole cannot grow indefinitely, practical and theoretical barriers begin to emerge that suggest even these monsters may eventually hit a ceiling. The primary brake on their growth appears to be their own brilliant power. As a black hole feeds and its accretion disk shines with the ferocity of a quasar, the intense radiation it generates exerts an outward pressure on the surrounding gas and dust. This radiative feedback can effectively blow away the black hole's own food supply, acting as a cosmic thermostat that prevents it from consuming everything in sight. There is a theoretical maximum rate at which a black hole can steadily accrete matter, known as the Eddington limit, beyond which the radiation pressure overcomes gravity and pushes material away. While black holes might experience brief periods of super-Eddington accretion, especially in the chaotic early universe, sustained growth at this rate is difficult. For a black hole to reach the mass of ton 6 akin in the time available, it would have needed to consistently feed at or near this extreme limit for hundreds of millions of years, a feat that requires a perfect and nearly uninterrupted delivery of fuel, a scenario that pushes the boundaries of what we believe is cosmologically possible. Beyond the challenge of simply gathering enough material, the immense scale of these objects may hint at the need for entirely new physical processes. Our current models of black hole formation and growth are built upon Einstein's general relativity and standard models of cosmology. Yet, when we plug the observed properties of ton 6 akin into these equations, the numbers can seem almost too extreme. To form so early in the universe, it must have started from a seed of staggering proportions, either a direct collapse, black hole of unprecedented size, or a runaway chain of mergers in an impossibly dense environment. The sheer gravitational influence of a black hole this massive could also begin to affect the structure of space-time and the expansion history of the universe on local scales in ways we are only beginning to theorize about. Some physicists speculate that in the environments around these ultramassive black holes, the effects of quantum gravity, a theory that successfully unites general relativity with quantum mechanics, might become noticeable. While we are far from detecting such effects, the existence of ton 6 akin and its ilk serves as a glaring, bright beacon pointing toward the potential limits of our current understanding and the possible need for a more complete, unified theory of physics. This search for the ultimate upper mass limit is an active and thrilling area of astronomical research. The current record holders, like ton 6 akin and the potential 100 billion solar mass black hole in IC 1101, may not be the final word. As our telescopes peer deeper into the cosmos, we could yet discover even larger gravitational Goliaths. However, a fascinating possibility is that the greatest black holes are not found in the present-day universe at all, but existed in the distant past. The peak era for black hole growth was likely during the universe's youth, around 10 billion years ago, when galactic collisions were common and vast reservoirs of dense gas were available for feasting. It is conceivable that the most massive black hole that will ever exist has already lived and died, its immense event horizon having evaporated over an eternity via Hawking radiation, a process so slow that for any black hole of this size, the universe is far, far too young for even a fraction of its mass to have dissipated. The hunt for these ultimate giants is more than a cosmic record-keeping exercise. It is a direct test of our models of cosmic evolution. Finding a black hole significantly more massive than ton 6 akin would force a major revision of our theories of accretion and feedback, while an apparent cutoff in the black hole mass function would provide crucial evidence for the ultimate dominance of the feedback processes that govern galaxy growth. These dark hearts, therefore, are not just endpoints of stellar evolution. They are the critical probes with which we can stress-test our understanding of the universe, from its grandest scales to its most fundamental laws. But the gravitational influence of these cosmic giants extends far beyond their event horizons and glowing accretion disks, warping the very pathways that light must travel through the cosmos. This brings us to one of the most visually stunning consequences of Einstein's general relativity, a phenomenon known as gravitational lensing. At its heart, the concept is deceptively simple. Massive objects warp the fabric of spacetime, and since light always travels along the straightest possible path through this curved geometry, its trajectory gets bent. A supermassive black hole, with its unimaginable density, creates one of the most severe gravitational wells in the universe, acting as a natural, albeit chaotic, cosmic telescope. When a distant galaxy, quasar, or any luminous object lies directly behind a black hole from our viewpoint on Earth, the black hole's gravity doesn't just slightly deflect the light. It can twist, smear, and multiply it into a celestial carnival of illusions, creating multiple images, bright arcs, and even complete rings of light known as Einstein rings. To visualize this, imagine placing a heavy bowling ball in the center of a perfectly stretched rubber sheet. This creates a deep, smooth indentation. Now, roll a tiny marble from one edge of the sheet toward the other, passing near the bowling ball. The marble won't travel in a straight line. Its path will curve as it rolls through the warped surface. Light behaves in much the same way. When the light from a distant star travels across the universe and passes near a supermassive black hole, it doesn't simply fly past in a straight line. It follows the curvature of spacetime created by the black hole's mass. From our perspective, it appears as if the light has been bent around the black hole. In cases of perfect alignment where the background object, the black hole, and our telescope are in a straight line, this bending can wrap all the way around the black hole, forming a complete or nearly complete circle of light, an Einstein ring. This ring is not a real structure. It is a perfect mirage, a single image of the background object duplicated and stretched into a brilliant halo encircling the darkness of the black hole itself. The practical applications of this phenomenon are as profound as the visuals are beautiful. For astronomers, gravitational lensing is not just a curious optical effect. It is a powerful tool for cosmic discovery. One of its most crucial uses is in the act of weighing the lens itself. By carefully measuring the separation and brightness of the multiple images created by the lensing effect, scientists can perform a direct calculation of the mass responsible for the warping. This provides an independent and highly accurate method to measure the mass of the supermassive black hole and the entire galaxy cluster it anchors, confirming the estimates derived from stellar orbits and gas dynamics. It's a cosmic scale that relies on nothing but the immutable laws of gravity and the behavior of light. Furthermore, the lensing effect acts as a natural magnifying glass. The bending of light rays effectively concentrates them, amplifying the brightness of the background source. This allows us to see galaxies that are otherwise too distant and faint for our telescopes to detect directly. Through the gravitational lens of a foreground black hole or galaxy cluster, we can peer deeper into the cosmos than ever before, observing the first generations of galaxies that formed after the Big Bang. Perhaps the most mysterious application of this principle involves the search for the invisible. Not all lensing events are caused by objects we can see. Sometimes, astronomers observe a distant star suddenly and mysteriously brighten for a period of time, with a very specific light curve that perfectly matches the signature of gravitational lensing. Yet, when they look at that region of space, there is no visible object massive enough to cause the distortion. The only explanation is a lone, dark object of significant mass passing between us and the star. These unseen lenses could be a population of isolated stellar mass black holes, neutron stars, or even free-floating planets wandering the interstellar void. By studying these microlensing events, we are effectively conducting a census of the universe's dark, invisible population, mapping the unseen architecture of our galaxy. Gravitational lensing, orchestrated by the most destructive objects in the cosmos, thus becomes one of our most creative and versatile instruments for exploring the universe, allowing us to weigh the invisible, magnify the unreachable, and ultimately see the unseen. We have spent this entire journey outside the event horizon, observing the brilliant light shows and the warping of space-time from a safe distance. But now we must confront the ultimate, unanswerable question: what actually happens to the stuff that falls in? When a star, a cloud of gas, or an unlucky astronaut crosses that final boundary, where does it go, and what is its final state? According to our best current understanding, rooted in Einstein's theory of general relativity, the journey does not end at the event horizon. That boundary is merely the doorway. Once inside, the inward pull is still absolute, and the destination is a place of such profound extremity that our laws of physics simply give up and stop working. This is the singularity, the theoretical heart of the black hole, where matter is thought to meet its ultimate and most bizarre fate. The path inward from the event horizon is a one-way trip of increasing violence and distortion. Inside a non-spinning black hole, every possible path for a particle, every trajectory through space-time, points inexorably toward the center. There is no stopping, no orbiting, no turning back. The matter that has crossed the horizon is not just falling. It is being relentlessly compressed from all sides as space itself collapses inward toward a central point. Imagine being in a room where the walls, the floor, and the ceiling are all rushing toward you at the speed of light, and you are rushing toward them just as fast. This is the environment inside a black hole. All the material that has ever fallen in, the gas, the dust, the stars, the planets, is being funneled and squeezed into an ever-diminishing volume, its density skyrocketing to values that have no analog anywhere else in the universe. General relativity predicts that this collapse does not stabilize. It continues unabated, with all the infalling matter and energy being crushed into a single point of infinite density and zero volume. This is the singularity. The word itself is a placeholder for our ignorance, a mathematical term for a place where the equations of gravity produce infinities, signaling that the theory has reached its breaking point. At the singularity, concepts like space and time as we know them cease to have any meaningful definition. The curvature of space-time becomes infinite, and the gravitational tidal forces, which we already know are strong enough to spaghettify a star, become infinitely strong. Any object, no matter how robust, would be torn down to its most fundamental constituents, and then what? We don't know. The physics simply does not provide an answer. It's as if the universe has a divide by zero error at its very core. This idea of a singularity is so strange that it is helpful to think of it not as a place in space, but as a moment in time. From the perspective of the matter falling in, the singularity is not a location you arrive at. It is a future event that you cannot avoid, much like tomorrow is an event in your future. Your timeline, from the moment you cross the event horizon, is on a collision course with this final moment. When you reach it, your existence, in any form we can describe with physics, simply ends. Your mass and energy are added to the total that defines the black hole. But the intricate information that was you, the arrangement of your atoms, your memories, your structure, is, according to classical relativity, irretrievably lost to the infinite gravity of the singularity. Of course, physicists are deeply uncomfortable with the concept of a true infinity in nature. It is almost universally believed that the singularity is not the final word, but rather a sign that we need a more complete theory, a theory of quantum gravity that can successfully merge the large-scale rules of general relativity with the small-scale weirdness of quantum mechanics. In the quantum realm, the Heisenberg uncertainty principle might prevent matter from being compressed into a true point of zero volume. Perhaps there is a smallest possible size, a fundamental graininess to spacetime that halts the collapse and forms an incredibly dense, but not infinitely dense, object sometimes called a Planck star or a fuzzball of vibrating strings, depending on the theoretical approach. While we lack the experimental evidence or a full theory to confirm it, the prevailing belief is that the classical singularity predicted by Einstein's equations is smoothed out by quantum effects, replacing a point of infinite doom with a physical state of matter so exotic that it defies our current imagination. The true fate of matter inside a black hole remains one of the greatest unsolved problems in all of physics, a dark secret hidden behind the ultimate veil, waiting for a genius to unite the theories of the very large with the very small, and finally reveal what lies at the center of cosmic darkness. But as we chart the immense gravitational influence of these supermassive black holes, we begin to brush up against an even deeper and more pervasive cosmic mystery. The matter we see swirling in accretion disks and the stars whipping around galactic centers represent only a tiny fraction of what's actually out there. The overwhelming majority of the universe's mass is invisible, a ghostly substance known as dark matter. This unseen material forms vast, spherical halos that envelop every galaxy, providing the gravitational scaffolding upon which visible structures are built. And now, scientists are beginning to ask a profound question. Could there be a hidden dialogue, a secret relationship, between the universe's most dominant dark component and its most powerful visible objects? The potential connection between supermassive black holes and dark matter is one of the most speculative and fascinating frontiers in modern cosmology. The most straightforward theory suggests that dark matter halos act as silent architects, indirectly governing the growth of the black holes at their centers. We know that a galaxy's dark matter halo is its primary source of gravity, far outweighing all the stars, gas, and dust combined. This immense, invisible structure dictates how the visible matter moves and collects. In the chaotic early universe, the depth of the dark matter's gravitational well would have determined how much ordinary gas could fall inward to fuel the nascent galaxy and its central black hole seed. A larger, more massive dark matter halo would have pulled in more gas, creating a richer feeding ground and allowing the central black hole to grow more rapidly. In this view, the correlation we see between black hole mass and galactic bulge might actually be a secondary effect. Both the bulge and the black hole could be tracing the primary driver, which is the mass of the invisible dark matter halo. The supermassive black hole, then, might not be directly linked to the stars we see, but rather to the immense, unseen ocean of dark matter in which the entire galaxy is floating. But the interaction could be far more direct and dynamic. Another compelling theory ventures into the realm of particle physics, proposing that certain types of dark matter particles could be their own antimatter counterparts. These so-called self-annihilating dark matter particles, when they collide with one another, would obliterate each other in a flash of energy, producing a shower of gamma rays, neutrinos, and other standard model particles. And where would you find the highest density of dark matter in a galaxy? Right at the center, deep within the gravitational pull of the supermassive black hole. As dark matter particles orbit the galaxy, their paths would naturally bring them swinging close to the central black hole. While the dark matter wouldn't fall into an accretion disk in the same way as normal gas, it rarely interacts with itself or other matter. Its orbits could be dramatically altered and concentrated by the black hole's gravity. Some models suggest that the black hole's pull could focus these particles into an incredibly dense spike or cusp right at the galactic core. Within this ultra-dense spike, the rate of particle collisions would skyrocket. This would turn the region around the black hole into a powerful engine fueled not by infalling gas, but by the continuous annihilation of dark matter. The energy released from this process could be significant, potentially even rivaling the output of a traditional accretion disk. This presents a radical possibility. What if some of the faint, high-energy radiation we detect from the centers of otherwise quiet galaxies isn't from sparse amounts of gas at all, but is the direct signature of dark matter annihilating itself in the black hole's intense gravitational field. This could explain persistent, unexplained gamma-ray signals from regions like the center of our own Milky Way, offering a potential way to finally detect dark matter not in a laboratory on Earth, but by observing the environment around a supermassive black hole. Exploring this connection forces us to confront the ultimate nature of both dark matter and gravity itself. If dark matter does indeed play a crucial role in seeding and feeding the earliest supermassive black holes, it would solve a major problem in our cosmic timeline, providing a natural mechanism for how these giants grew so big so quickly. Alternatively, if we could confirm that dark matter annihilation is a significant energy source, it would revolutionize our understanding of galactic cores and provide the first tangible clues about the properties of the dark matter particle. The supermassive black hole, once seen as a mere consumer of light, may instead be a brilliant beacon, illuminating the properties of the universe's most elusive substance and guiding us toward a deeper, more unified understanding of the dark and the light that shape our cosmos. Now, we turn our gaze from the established giants of the local universe to the cosmic dawn, to an era just a few 100 million years after the Big Bang, where the seeds of these monsters first took root. Observing this ancient epoch has always been the ultimate challenge. The light from the first galaxies and quasars has been stretched by the universe's expansion over billions of years, shifting from visible light into the far infrared part of the spectrum. For previous telescopes, this light was too faint, too red-shifted, and too obscured by cosmic dust to see clearly. This is precisely where the James Webb Space Telescope enters the story, not as just another observatory, but as a revolutionary machine designed to be a true time machine, built to witness the universe's first light and finally confront the infancy of supermassive black holes. Webb's transformative power lies in its specialized design, which is perfectly tailored for this specific archaeological dig into the early cosmos. Unlike the Hubble Space Telescope, which primarily sees in visible and ultraviolet light, Webb is a giant infrared telescope. Its 6.5-meter primary gold-coated mirror is the largest and most sensitive ever sent into space, acting as a colossal light bucket to gather the incredibly faint whispers of infrared radiation from the edge of time. It is also stationed 1 million miles from Earth at the second Lagrange point, a gravitationally stable location where it can operate in profound cold and darkness, shielded from the heat and light of both our planet and the Sun. This is critical because infrared is essentially heat radiation. To detect the faint heat signatures from the first galaxies, the telescope itself must be incredibly cold. Webb's instruments operate at a frigid -267 degrees Celsius, only a few degrees above absolute zero, allowing it to see the universe in exquisite infrared detail without being blinded by its own warmth. So, what does this mean for hunting the earliest black holes? It means Webb can cut through the cosmic dust that has obscured our view for decades. When the first galaxies were forming, they were often enshrouded in thick clouds of dust and gas, the very raw materials for star and black hole formation. This dust blocks visible light, but infrared light, with its longer wavelengths, can pass straight through it. Webb pulls back this dusty veil, revealing the stellar nurseries and chaotic cores of these infant galaxies for the first time. Furthermore, the extreme red shift means that the ultraviolet light emitted by the brilliant accretion disks of the earliest quasars has been stretched, or red-shifted, all the way into the infrared by the time it reaches us. A quasar that shone with fierce ultraviolet light 13 billion years ago arrives at Webb's mirrors as a faint infrared beacon. The telescope is, in effect, tuning into the correct frequency to hear the universe's opening notes, allowing it to conduct a census of black holes in the first billion years of cosmic history, a period that was previously almost entirely opaque to us. With this unprecedented vision, Webb is actively testing the two great theories for the origin of supermassive black holes: the direct collapse model, and the rapid growth from stellar remnants. It is searching for the telltale signatures of both. For the direct collapse model, astronomers are looking for galaxies that are surprisingly bright in infrared light, but show no signs of the heavy elements forged in generations of stars. A galaxy without these elements would be a pristine relic from the very first structures, and if it also contains a bright, compact core, that could be the signature of a massive black hole seed forming directly from a giant gas cloud, skipping the star-forming stage entirely. On the other hand, Webb is also hunting for the smaller, dimmer black holes that would represent the stellar remnant seeds. By peering into the hearts of the very first small dwarf galaxies, it can look for the faint X-ray emission or the subtle gravitational influence of black holes weighing just a few hundred or thousand solar masses. Finding a population of these smaller seeds would strongly support the bottom-up growth theory. The early results from Webb have been nothing short of breathtaking, delivering surprises that are already forcing scientists to refine their models. The telescope has confirmed the existence of fully formed supermassive black holes in galaxies at even earlier times than previously thought possible. It has found massive, bright galaxies and active black holes in a universe that, according to some predictions, should have been too young to host such mature structures. Some of the early quasars discovered appear to be so massive and so bright that they are challenging the very limits of our accretion physics, potentially requiring periods of hyper-efficient feeding that push past the theoretical Eddington limit. Every new image and spectrum from Webb is a new piece of evidence in this cosmic courtroom drama, helping us to judge which formation pathways were most common and ultimately, how the universe managed to construct its most powerful gravitational engines in the blink of a cosmic eye. This is not just about cataloging ancient objects. It is about rewriting the origin story of the cosmos itself, and in doing so, understanding the fundamental processes that gave rise to the galaxies and even the planets and life that we see around us today. Now we arrive at a truly spectacular and inevitable consequence of the cosmic building process we've been exploring: the existence of binary supermassive black holes. Throughout cosmic history, galaxies have been colliding and merging, a fundamental part of their growth. We see the evidence everywhere in the sky: distorted galaxies with long tidal tails, pairs of galaxies looking like celestial dancers caught in a slow-motion embrace. When these vast stellar metropolises merge, the most dramatic event isn't just the mingling of billions of stars. It's the fate of their dark, beating hearts. According to our models, every major galaxy merger should eventually result in the two central supermassive black holes forming a bound pair, a binary system, locked in a gravitational dance that can last for billions of years. Gravity initially draws these two titans together. As the galaxies intertwine, their central black holes, once separated by tens of thousands of light years, sink toward the new, merged galactic core through a process known as dynamical friction. They interact gravitationally with the background sea of stars and dark matter, losing energy and spiraling inward. Eventually, they get close enough, within a few light years, to feel each other's direct pull and form a true binary system. At this point, they are the most massive couple in the universe, two gravitational pits orbiting a common center of gravity. But then, their inward spiral can slow to a crawl, entering what astronomers call the final parsec problem. To get close enough to merge, they need to shed even more orbital energy, but in the vast, relatively empty region at the very center of a galaxy, there are often not enough stars or gas to provide the necessary friction. For a long time, it was a theoretical possibility that many supermassive black holes could become stuck in this wide binary state, orbiting each other for eons without ever colliding. So, how do we find evidence for these elusive cosmic couples? We can't see them directly, so astronomers have to look for the indirect, telltale signs of their presence. One of the most compelling methods involves observing the light from quasars. If a binary pair is actively feeding, the accretion disk around one or both black holes can produce a regular, periodic signal. Imagine a lighthouse with two beams rotating at different speeds. The combined light would flicker in a complex but predictable pattern. Scientists have scanned through vast archives of quasar data, looking for these periodic brightness variations. In several promising candidates, they've found quasars that flare up with a consistent rhythm, repeating every few years. The most straightforward explanation for this regular heartbeat is that the quasar's brightness is being modulated by the orbital motion of a second, unseen supermassive black hole tugging on the first, a cosmic clock ticking away in the heart of a distant galaxy. Another, even more dramatic signature comes from the study of supermassive black hole jets. In a few extraordinary systems, astronomers have observed jets that are not straight, but twisted into a spectacular corkscrew or helical shape. This is a powerful hint that the black hole powering the jet is not sitting still, but is itself wobbling or precessing as it moves through space. The most natural explanation for this wobble is that it is being gravitationally yanked around by a massive companion in a tight orbit. It's as if you were watching a garden sprinkler that was not only spraying water, but also being swung around in a circle, creating a spiral pattern. These kinked and curling jets are some of the most visually striking evidence we have that binary supermassive black holes are not just theoretical, but are real objects lurking in the centers of merged galaxies. The ultimate fate of these binaries is where the story reaches its breathtaking climax. If the black holes do manage to overcome the final parsec problem, through further interactions with gas or stars, their orbit will tighten until they are just a few hundredths of a light year apart. At this minuscule distance, their orbital periods shrink to just a few years, then months, then days. As they whip around each other at a significant fraction of the speed of light, they begin to lose energy in a new and dramatic way, by rippling spacetime itself. They become an immense source of gravitational waves, the same phenomena detected from stellar mass black holes by LIGO and Virgo, but at a vastly different, lower frequency. For millions of years, this binary chirp would be too low for any terrestrial observatory to hear. But in the final, furious moments before merger, when their event horizons are just about to touch, the frequency of the gravitational waves will sweep upward into the detectable band of a future space-based observatory like LISA. The collision of two supermassive black holes will be the single most energetic event in the universe since the Big Bang, releasing more power in gravitational waves, for a brief instant, than the combined light of every star in every galaxy in the observable universe. This won't be a flash of light. It will be a silent, shattering tremor in the fabric of reality, an event that will literally stretch and squeeze the space within our entire solar system as the waves pass through, a testament to the violent, dynamic, and interconnected nature of a cosmos built through collision. Now, we must grapple with one of the most radical and philosophical ideas to emerge from the clash between gravity and quantum mechanics, a concept that redefines our very notion of reality. This is the holographic principle, and it proposes a solution to the information paradox so elegant and strange that it feels more like science fiction than hard physics. The principle dares to suggest that our perception of a three-dimensional universe might be a magnificent illusion, a grand projection of information that is actually stored on a distant, two-dimensional surface. To understand how this could possibly work, it's helpful to think about an ordinary hologram like the kind you might see on a credit card. That shimmering, three-dimensional image isn't truly three-dimensional. It is encoded on a flat, two-dimensional piece of film. The holographic principle applies this same logic to the cosmos itself, proposing that our entire universe, with all its stars, galaxies, and black holes, could be a vast holographic projection. When we apply this mind-bending idea to a black hole, it directly tackles the paradox of lost information. The puzzle, as we've seen, is that general relativity says all the intricate details of matter falling into a black hole are destroyed at the singularity, while quantum mechanics insists this information must be preserved. The holographic principle offers a way out. It suggests that the information about every single particle that falls into the black hole is not lost inside the singularity at all. Instead, as an object crosses the event horizon, a perfect, pixel-like copy of all its information is instantly imprinted or encoded onto the two-dimensional surface area of the event horizon itself. Imagine the event horizon not as a smooth, featureless boundary, but as an incredibly dense and complex hard drive, storing the complete quantum description of everything that has ever fallen in. The three-dimensional interior of the black hole, with its unfathomable singularity, is not where the real story is happening. It is merely a projection, a shadow of the information painted on the two-dimensional surface that encloses it. This leads to a startling implication about the fundamental nature of space. If the information about the volume inside a black hole can be stored on its surface, then perhaps the very concept of a third dimension is redundant. The true, fundamental degrees of freedom in the universe might operate in two dimensions, and the three-dimensional world we experience is an emergent property, a holographic movie playing out on a cosmic screen. The mathematics behind this comes from studying the thermodynamics of black holes, where physicists found that the maximum amount of information a region of space can contain is not proportional to its volume, as our intuition would suggest, but to the surface area of its boundary. For a black hole, this means the information capacity of its entire interior is dictated solely by the size of its event horizon. It's as if a book's entire contents were determined not by the number of pages it has, but by the area of its cover. So, how does this solve the information paradox? The key lies in the nature of Hawking radiation. In the standard picture, this radiation is random and thermal, carrying no information. But if the holographic principle is correct, then the Hawking particles that slowly leak out are not created from nothing near the horizon. Instead, they are directly linked to the information bits stored on the event horizon's surface. As the black hole evaporates, its surface area shrinks, and the encoded information is subtly transferred to the outgoing radiation. It's an incredibly complex and scrambled process, like burning an encyclopedia and trying to read its contents by analyzing the smoke and ash. The information is not lost. It is transformed and redistributed back into the universe in a form that is practically impossible to decode, but it is, in principle, preserved. This means that if you could somehow collect every last photon of Hawking radiation from a black hole's complete evaporation, and had a computer of infinite power to analyze it, you could, in theory, reconstruct the entire history of everything that ever fell in. The black hole is not a cosmic shredder. It is the ultimate cryptographic device, and the holographic principle ensures that no page of the cosmic story is ever truly torn out and destroyed. Having journeyed to the edge of reality to understand the formation, power, and profound mystery of these cosmic giants, it's only natural for our minds to turn inward, to our own fragile, pale blue dot in the vastness. It's a question born of both primal fear and cinematic spectacle. Could the terrifying power of a supermassive black hole, capable of shredding stars and swallowing solar systems, ever reach out and threaten our world? The short and definitive answer is no, and the reason for our safety lies not in some cosmic force field, but in the most fundamental and humbling property of the universe itself, its sheer, incomprehensible scale. The distances between celestial objects are so staggeringly vast that they act as the ultimate quarantine, isolating us from the universe's most extreme events and ensuring our cosmic neighborhood remains remarkably peaceful. Consider our own galactic anchor, Sagittarius A star. This 4 million solar mass giant resides at the very heart of the Milky Way, a distance of approximately 26,000 light-years from Earth. To grasp what that truly means, let's break it down. A single light year is the distance light travels in 1 year, moving at the uncontested cosmic speed limit of about 299 million meters per second. That's nearly 10 trillion kilometers. Multiply that by 26,000, and you have a number so large it becomes abstract. If you were to embark on a journey to our galactic center in the fastest spacecraft ever built by humanity, it would take you over 450 million years to arrive. This isn't just a long trip. It's a time span that dwarfs the entire existence of complex life on our planet. The supermassive black hole is not just far away. It is, for all practical human purposes, infinitely remote. A distant monarch ruling a kingdom we can only observe from the most distant provinces. This immense separation grants us a profound and absolute safety. The gravitational influence of any object, even one as massive as Sagittarius A star, weakens with the square of the distance. From our vantage point 26,000 light-years away, the gravitational pull from our central black hole is utterly negligible. It does not tug on our planet. It does not destabilize our solar system's orbit. In fact, the Sun's own gravity is what holds us in a firm embrace, and it does so with a grip that is more than a trillion times stronger at our location than the pull from the black hole at the galactic center. We are not in some slow, invisible spiral toward our doom. We are in a stable, predictable orbit around the galaxy, just like billions of other stars, a dance that has continued for billions of years and will continue for billions more. The real cosmic danger from a black hole comes from venturing extremely close to its event horizon, a scenario that is simply impossible given our fixed and distant location. Even the most violent tantrums of an active black hole pose no threat to us. We've discussed quasars and the immense relativistic jets that can shoot out across intergalactic space. While these jets are indeed powerful enough to sterilize entire galaxies, they are also incredibly narrow, like the beam of a cosmic laser pointer. For such a jet to threaten Earth, two incredibly unlikely events would need to occur simultaneously. First, a dormant black hole like Sagittarius A star would need to be reignited into a brilliant quasar, which requires a massive and sudden infusion of gas, an event that is not occurring in our current galactic era. Second, and far more improbably, our solar system would have to be perfectly aligned within the infinitesimally narrow cone of one of these jets as it fired. Given that a jet width is a tiny fraction of a degree, and our position in the galaxy is entirely random relative to the black hole's spin axis, the odds of this happening are so astronomically low as to be effectively zero. The universe is not a carefully aimed sniper rifle. It is a chaotic but largely empty expanse where direct, catastrophic hits from such focused phenomena are vanishingly rare. The true existential threats to our planet are far more local and mundane. A large asteroid impact, a supervolcanic eruption, or the long-term consequences of our own actions on the climate are all immeasurably more probable and immediate dangers than any hypothetical scenario involving a distant black hole. This perspective is not meant to minimize those terrestrial concerns, but to provide a profound sense of cosmic context. It underscores a beautiful and reassuring truth about our place in the cosmos. We live in a universe that is both breathtakingly violent and majestically serene. The supermassive black holes that shape galaxies and power quasars are the architects of the large-scale cosmic structure. But they operate on a stage so grand that our entire world is but a fleeting, unnoticed speck in the audience. They are the forces that build and destroy on galactic timescales, while we inhabit a quiet, stable corner where life has been granted the eons necessary to arise, evolve, and ponder the very darkness that, from an impossible distance, made our existence possible. Our safety is woven into the fabric of space itself, a gift of cosmic geography that allows us to study these magnificent monsters from the safety of our own front porch, forever observers of the sublime and terrible beauty of the universe. And so our journey through the shadowed hearts of galaxies draws to a close. A voyage that has taken us from the serene orbits of stars around our own quiet giant, Sagittarius A star, to the ravenous, hyper-luminous feast of Tun 618, a colossus whose mass defies easy comprehension. We have stood at the edge of probability, peering into the fiery rings captured by the Event Horizon Telescope, and ventured into the theoretical abyss of singularities and holographic horizons. We have witnessed how these gravitational titans are not mere endpoints of collapse, but active architects of the cosmic landscape. Their powerful feedback and magnetically driven jets sculpting galaxies and regulating the birth of stars across eons. From the mysterious seeds of the early universe, glimpsed by the James Webb Space Telescope, to the slow, gravitational wave-inducing dance of binary pairs, we have uncovered a story of constant, dynamic, and often violent change written in gravity and shadow. This exploration reveals something fundamental about our place in the cosmos. We inhabit a universe where the most profound forces are often hidden in plain sight, operating on scales of space and time that dwarf human experience. The existence of supermassive black holes challenges us to think bigger, to push our understanding of physics to its very limits, and to accept that reality is far stranger and more wonderful than our everyday lives would suggest. They are the ultimate natural laboratories, testing grounds for our theories of gravity, quantum mechanics, and the very nature of information itself. Every new discovery, from a quiet black hole in a dwarf galaxy to the faint hum of a gravitational wave background, peels back another layer of this magnificent mystery, reminding us that the quest for knowledge is a never-ending journey to the edge of the known. As we reflect on this mind-expanding tour, from the immense scales to the profound influences on the structure of everything we see, it is clear that these enigmatic objects are more than just cosmic curiosities. They are the dark, beating hearts around which the story of the universe is written. They push the boundaries of human knowledge, forcing us to confront the deepest questions about space, time, and our own existence within this vast, interconnected tapestry. Now, we turn the reflection over to you. Of the 30 incredible facts we have explored together, which one reshaped your perspective the most? Was it the sheer, unimaginable scale of Tun 618's event horizon, the elegant horror of a star being tidally disrupted, or the mind-bending possibility of the holographic principle? Share the fact that amazed you the most down in the comments below. We would love to continue this conversation with you. And if you are hungry for more journeys to the edges of understanding, be sure to subscribe and hit the notification bell so you will not miss our next deep dive into the great mysteries of space.